There is something in the universe so large that the words we use to describe size simply break down inside it. It is not a galaxy, it is not a cluster of galaxies, it is not even a cluster of clusters. It's something that stretches across the sky for 10 billion light years, perhaps 15 according to the most recent measurements, and contains so many galaxies that the number ceases to mean anything in particular. By every standard model of cosmology, it should not exist. And yet, when we look in a certain direction in the night sky, the data keep saying that it does. What follows is the slow, careful story of that structure. What it is, how it was found, why scientists keep arguing about whether it is real, and what its existence might tell us about a universe we are still in the early stages of understanding. If you find this kind of quiet exploration restful, consider hitting like and subscribing. It helps more than you might think. Now, let's begin. The structure has a name that sounds more like a postal address than a cosmic wonder. The Hercules Corona Borealis Great Wall. It was named in part by a Filipino teenager on the internet, which is a detail we will come back to. The structure was first identified in 2014 by a small team of Hungarian and American astronomers, working not with images of galaxies but with maps of the most violent explosions in the universe. The structure they identified, based on the way these explosions were clustered across one region of the sky, was, at the time, the largest single object ever proposed in astronomy. It still is. The size is the part that does not fit. The Hercules Corona Borealis Great Wall is approximately 10 billion light-years across at its longest dimension. Some recent measurements suggest it may be as large as 15 billion. The observable universe itself is only about 93 billion light-years in diameter, which means this single structure spans somewhere between 1/10 and 1/6 of everything we can possibly see. To put that in different terms, the light arriving at our telescopes from one end of the Great Wall left its source roughly when the Sun and the Earth had not yet been formed. The light from the other end is younger, but still ancient. The object that connects these two endpoints is so vast that no single coherent image of it has ever been made, or could ever be made. We see it in pieces, in statistical patterns, in the way certain rare events cluster across the sky. The reason the structure should not exist has nothing to do with poetry. It has to do with mathematics. The standard model of cosmology, the framework that has been refined over a century of careful work and that explains most of what we observe in the universe, predicts that very large structures should not be able to form within the time available. The universe is approximately 13.8 billion years old. Structures grow by gravitational attraction, drawing matter together from initially small fluctuations in the early universe. The growth is slow, and the maximum size that any single structure should be able to reach in 13.8 billion years is approximately 1.2 billion light-years. Anything larger than that should not have had enough time to assemble. The Hercules Corona Borealis Great Wall is roughly 10 times larger than that limit. Some interpretations push it toward 15 times larger. The standard model does not break gently in the face of this. It is not a small statistical excess. It is a major anomaly, and astronomers have spent more than a decade now arguing about what to do with it. The arguments take several forms. Some researchers question whether the structure is really there at all, whether it might be a kind of statistical illusion produced by the way gamma-ray bursts happen to be distributed, or by gaps in the data, or by various subtle observational biases. Other researchers accept that the structure is real, but propose that the standard cosmological model is missing something. Perhaps the rules governing structure formation in the early universe were different from what we currently model. Perhaps there are physical processes operating at very large scales that we have not yet identified. Perhaps the cosmological principle itself, the assumption that the universe is essentially the same in all directions and at all locations, is only approximately true. The honest answer, as of the time of this recording, is that no one knows. The Great Wall sits in the data, persistent and enormous, refusing to resolve neatly into any of the explanations that have been proposed for it. It might be telling us something important about the universe. It might be telling us something important about the limits of our measurements. The most interesting possibility is that it is doing both. For now, it is simply there, an object so large that we struggle to call it an object at all. 10 billion light-years of cosmic structure, far older than any star you have ever seen, drifting quietly through the same universe in which you are listening right now to this recording. It is worth pausing on that last phrase, the same universe. The Great Wall is not a separate cosmos. It is in this universe, the one you are in, and the light from it is arriving at instruments in orbit around the Earth at this very moment. Every second of every day, photons that left galaxies inside the Great Wall 10 billion years ago complete their journey by being absorbed into the detectors of satellites that human beings designed and built and launched into space. The record of those arrivals is what gave the wall away. The data is real, the structure is real, and the strangeness of its existence is not a literary effect added to make the story more dramatic. The strangeness is in the science itself. Numbers at cosmic scales tend to lose their meaning quickly. The mind, which evolved to track berries and predators and the spatial layout of small villages, was not designed to feel the difference between a billion and a trillion. So before we go any further into the story of this structure, it is worth slowing down and building a sense of what we are actually talking about. Not in numbers alone, in something closer to images. Begin with the Milky Way. Your home galaxy is approximately 100,000 light-years across. That number alone is already difficult to feel. 1 light-year is the distance that light travels in a year, at 300,000 kilometers per second. A spacecraft traveling at the fastest speed any human-made object has ever achieved. The Parker Solar Probe, at its closest approach to the Sun, would take roughly 7,000 years to cross a single light-year. To cross the full diameter of the Milky Way at that speed would take 700 million years. That is one galaxy, your galaxy. Now imagine 10 of them lined up end to end. The distance you have just traversed in your imagination is 1 million light-years. This is close to the distance between our Milky Way and the Andromeda Galaxy, our nearest large neighbour. Light leaving Andromeda tonight will arrive at Earth in approximately 2.5 million years. You will not be here to see it. Neither will any of your descendants for hundreds of thousands of generations. Now extend the line to 10,000 Milky Ways. The distance is 1 billion light-years. This is larger than any single bound structure in the standard cosmological model. It is comparable to the size of the largest galaxy superclusters, vast collections containing many thousands of galaxies bound together by gravity. The Laniakea supercluster, which is the local cosmic neighbourhood that contains our Milky Way, along with approximately 100,000 other galaxies, is about half this size. Now extend the line further, to 10 billion light-years. You are now within range of the actual size of the Hercules Corona Borealis Great Wall. The line you have just imagined contains, in linear extent, 100,000 Milky Ways laid end to end. The title of this recording, with its mention of 10,000 Milky Ways, was modest. The actual scale is 10 times that. We chose the smaller number because it remains within some recognisable boundary of comprehension. The true number begins to slip out of human reach entirely. But the Great Wall is not a line. It has width and depth as well as length. Its width is roughly 7 billion light-years, and its thickness is approximately 1 billion light-years. The total volume of space it occupies, considered as a single connected region, contains an estimated several 100,000 galaxy groups and clusters, each of which contains thousands of galaxies, each of which contains hundreds of billions of stars. The number of stars within the Great Wall is, for all practical purposes, uncountable. Astronomers do not usually try to count it. They estimate the matter content statistically, through measurements of how that matter affects the light passing through and around it. There is something soothing about this scale, though it takes a moment to feel why. The structure does not move, it does not consume, it does not threaten, it simply is. It has been quietly arranged across this enormous region of space for a long time before anything resembling Earth existed, and it will continue to be arranged there for a long time after Earth is no longer recognizable as such. Its existence is not aimed at us. It does not require us to notice it. It is simply part of the architecture of the universe in which we happen to live. When you look up at the night sky from a dark location on a clear evening, you cannot see the Great Wall. The light from its individual galaxies is far too faint to be visible to the naked eye, even when those galaxies are concentrated into vast filaments. What you see in the night sky is a tiny local sample, stars within our own galaxy. Perhaps the Andromeda Galaxy is a faint smudge if you know exactly where to look. The Great Wall is invisible to you in any direct sense, but it is there, and every night when you look upward, the light from a small portion of it is passing through the atmosphere above your head, travelling towards telescopes that are, at this very moment, recording the patterns that allow us to study a structure that should not exist. The size is more comfortable to feel than to count. So let it be felt. Let the number become an image. an image of something old and vast and quiet and arranged in ways that we are still learning how to see. To understand what the Hercules Corona Borealis Great Wall actually is, we have to step back and look at how matter is distributed throughout the universe more generally. The picture that has emerged over the past several decades, built up from sky surveys, computer simulations, and careful theoretical work, is one of the most beautiful results in modern cosmology. It is also one of the most counterintuitive. You might imagine that matter in the universe is spread out roughly evenly, like grains of sand scattered across a vast beach. This is approximately true at the very largest scales. Averaged over distances of billions of light years, the universe really does look fairly uniform. But at smaller scales, the scales of galaxies, clusters, and superclusters, matter is distributed in an extremely structured way. It clumps, it strings together, it forms patterns that look more like a network than like a uniform fog. This network is called the cosmic web. It is the largest pattern in the universe, and almost everything you have ever heard of in astronomy is somewhere within it. The web consists of three main components: filaments, walls, and voids. Filaments are long, thin strings of matter, often containing dozens or hundreds of galaxy clusters arranged in approximately linear sequence. Walls are flatter, broader sheets of matter, where filaments come together. Voids are the empty regions between filaments and walls, vast, nearly spherical regions of space where almost no galaxies exist at all. The voids are not perfectly empty, but their density is so low compared to the filaments that they appear, in maps of the universe, as dark holes punched through the lighter pattern of the cosmic structure. The Hercules Corona Borealis Great Wall is, by its name, classified as a wall, though in practice it is more of a complex filamentary structure with substantial thickness. It sits at the intersection of multiple filaments and is one of many such concentrations of matter throughout the cosmic web. What distinguishes it from the others is its sheer size. The cosmic web contains many features that are large by ordinary standards, but the Great Wall is so much larger than the others that it occupies a category essentially of its own. The cosmic web exists because of a combination of three factors. The first is the initial conditions of the universe. When the universe was approximately 380,000 years old, it had cooled enough for the first atoms to form and for light to begin travelling freely through space. The pattern of slight variations in density at that moment, captured by precise measurements of the cosmic microwave background radiation, is the seed pattern from which all later structure grew. The second factor is gravity. Regions that started slightly denser than average attracted more matter from their surroundings, growing more dense over time. Regions that started slightly less dense lost matter to their denser neighbours, becoming the voids. The third factor is the role of dark matter, which makes up the majority of the mass in the universe and provides the gravitational scaffolding around which visible matter has accumulated. The web is therefore a record of history. It is what the early universe looked like, expanded and amplified over 13 billion years by the steady action of gravity. When you look at a detailed map of the cosmic web, the kind produced by surveys like the Sloan Digital Sky Survey, which has catalogued millions of galaxies, you are looking at the slow evolution of the universe made visible. The patterns you see are not random. They are the consequence of physical processes operating across enormous spans of time, producing structures that range from the small to the unfathomably large. Within this context, VOAS, the Hercules Corona Borealis Great Wall, becomes both more and less remarkable. Less, because it is part of a larger pattern, not a unique object in some absolute sense, but an extreme example of a phenomenon that occurs throughout the universe at smaller scales. More, because its size pushes against the limits of what the cosmic web is supposed to produce. Most filaments and walls fall comfortably within the range that standard models predict. The Great Wall does not. It is the cosmic web's strangest expression, the place where the pattern that organizes the universe seems to push beyond its own rules. When astronomers map the Great Wall, what they are doing, in effect, is tracing one of the most extreme regions of this larger structure. The maps they produce are sparse and difficult to read. They depend on rare events, statistical methods, and inferences drawn from indirect measurements. But the pattern they reveal is real. It is part of the cosmic web, just like everything else. The question is why it is so much larger than the cosmic web should be able to make it. The most extraordinary thing about the discovery of the Great Wall is that it was made not by looking at galaxies, but by looking at the brief, brilliant flashes of light that occur when certain massive stars die. These flashes are called gamma-ray bursts, and they are, by a substantial margin, the most luminous events in the universe. A gamma-ray burst is an explosion of such extreme energy that, for the brief seconds or minutes during which it lasts, it outshines the entire rest of the observable universe at gamma-ray wavelengths. The bursts come in two main categories. Long-duration bursts, which last from a few seconds to several minutes, are believed to originate from the collapse of very massive stars at the end of their lives. The collapse produces a black hole, and the surrounding stellar material falls inward and is ejected at nearly the speed of light along narrow jets, producing the burst. Short-duration bursts, which last less than 2 seconds, are believed to result from the collisions of neutron stars or other dense stellar remnants. Both types release amounts of energy that exceed, in those brief moments, what most stars produce over their entire lifetimes. The relevance of gamma-ray bursts to the discovery of the Great Wall is that they are visible at enormous distances. The energy is so concentrated and so intense that it can be detected even when the source is many billions of light-years away. This makes gamma-ray bursts useful as cosmic markers, points of light that can be identified across most of the observable universe, allowing astronomers to map the distribution of matter at distances where ordinary galaxies become too faint to detect. The process works like this. When a gamma-ray burst occurs, telescopes in orbit around Earth, particularly NASA's Fermi Gamma Ray Space Telescope and the Neil Gehrels Swift Observatory, detect the burst within seconds of its arrival and pinpoint its location in the sky. Follow-up observations from ground-based telescopes are then conducted as quickly as possible to identify the host galaxy of the burst and to measure its distance. The distance is determined through the redshift of the host galaxy's spectrum, the stretching of light wavelengths due to the expansion of the universe between the time the light was emitted and the time it arrived at Earth. Higher redshifts correspond to greater distances and to earlier moments in cosmic history. By accumulating measurements of many gamma-ray bursts over many years, astronomers can build up maps of where these explosions occurred. The maps cover essentially the entire observable universe, including regions that are too distant for any ordinary galaxy survey to reach. Each burst represents a stellar death somewhere out there, in some galaxy, at some moment in cosmic history. The collective pattern of all these deaths traces the underlying distribution of matter from which the stars themselves originally formed. In 2014, a team of astronomers, led by Istvan Horvath of the National University of Public Service in Budapest, along with John Hackler of the College of Charleston and Zsolt Bergoli of Eötvös-Loránd University, analysed the available gamma-ray burst data and noticed something strange. The bursts were not evenly distributed across the sky. In one particular region, roughly in the direction of the constellations Hercules and Corona Borealis, at redshifts corresponding to about 10 billion years in the past, there was a substantial overdensity of bursts. The pattern was statistically significant. It could not easily be explained by random fluctuations in the data. The interpretation, as Horvath and his colleagues proposed it, was that this overdensity of bursts traced an underlying overdensity of matter. There were more gamma-ray bursts in this region of the sky because there were more galaxies there to produce them. The galaxies, in turn, were arranged in some kind of large coherent structure, a wall or filament of the cosmic web, but one substantially larger than any other such structure that had ever been identified. The discovery was published in 2014 and confirmed with additional data the following year. The structure was officially recognized as the Hercules Corona Borealis Great Wall, and it took its place in the astronomical literature as the largest known object in the universe. What makes this discovery method elegant, and also somewhat fragile, is that it depends entirely on the statistical clustering of rare events. There is no direct image of the Great Wall. There never has been. There never will be. The structure exists in the data only as a pattern, a region where, when you map gamma-ray bursts across the sky, you find more of them than the standard model predicts. The pattern is real, but it has to be inferred. It cannot be photographed. Most of what we know about the universe at very large scales depends on inferences of this kind. The Great Wall is an extreme example of a normal method, applied to data that turned out to be more interesting than anyone expected. Every astronomical object has a story behind its name. Some are named for the discoverer, some are named for the constellation in which they appear, some are named through formal processes administered by the International Astronomical Union, with committees and proposals and votes. And then there are the names that emerge from the internet, coined casually by people without official credentials, and adopted simply because they captured something about the object that nothing else quite did. The Hercules Corona Borealis Great Wall is one of the latter. The structure was discovered, as we have said, in 2014. The discovery paper by Horvath and colleagues did not give it a name. They simply described it as a clustering of gamma-ray bursts in a particular region of the sky. The structure did not have a name yet because no one had thought to give it one. The name came later, from a Filipino teenager named Jondrick Valdez. Valdez was an amateur astronomy enthusiast, the kind of teenager who reads scientific papers and updates Wikipedia articles in their free time. After reading about the new discovery, Valdez edited the Wikipedia article on the structure to give it a name based on the two constellations in which it appeared most prominently, Hercules and Corona Borealis. The name stuck. Other Wikipedia editors accepted the change. Subsequent news articles used the name. Eventually, even some scientific papers began to use it. By the time the structure was widely known to the public, it had a name that had originated not in a research institution or a discovery announcement, but in the Wikipedia edit history. There is something appropriate about this. The Great Wall is a strange object discovered through statistical methods that did not produce a clear image, located at a distance that places it nearly at the limit of what we can study. The discovery was made by a small team of researchers in 2 countries, working with data from satellites operated by yet other countries. The name was given by a teenager in the Philippines. The structure itself, considered as a phenomenon in the world, belongs to no one. It exists at distances and scales that have nothing to do with national borders or institutional affiliations. The casual, distributed, somewhat accidental way in which it acquired its name reflects the casual, distributed, somewhat accidental nature of how we have come to know about it. The name itself is also slightly misleading, which is worth noting. The Hercules and Corona Borealis constellations are the most prominent parts of the sky in which the structure appears, but the Great Wall actually extends well beyond those 2 constellations. Detailed maps show that the structure spans from the region of the constellation Boötes through Hercules, Corona Borealis, and into Gemini, covering a substantial portion of the northern celestial hemisphere. The name is therefore a kind of shorthand. It identifies the constellations where the structure is most concentrated, without claiming to describe its full extent. In this respect, the name is similar to many other names in astronomy. The Andromeda Galaxy is named for the constellation in which it appears from Earth's perspective, but the galaxy itself has no particular connection to Andromeda. The constellation is a feature of our line of sight, not of the galaxy. The galaxy would still exist and would have the same shape and the same stars if Earth and its mythology had never been here to assign the name. Names are useful for organizing our knowledge, but they are not properties of the things they name. The Great Wall would exist regardless of what we called it. It has existed for billions of years before anyone named anything at all. Jondrick Valdez, the teenager who proposed the name, has since become a more public figure in the astronomy community. He has been interviewed about his role in the naming and has discussed his interest in astronomy as a career. The story of how the name was given is now part of the broader narrative around the structure. A small detail that adds a human element to a story that is otherwise dominated by very large numbers and very abstract physics. There is a quiet lesson in this. The largest object in the universe was given its name by a teenager who edited Wikipedia in his spare time. The professionalization of science, the apparatus of institutions and grants and credentials, did not produce the name. A curious young person with internet access produced the name. The lesson is not that institutions don't matter, they obviously do, since the discovery itself was made by researchers using satellites built by national space agencies, but that the boundary between expert and amateur in astronomy is more porous than it sometimes appears. Discovery, naming, interpretation, communication, these activities flow across the boundary in many disciplines, and the result is a science that belongs to more people than just the ones with the official titles. The constellations are old. The names we give to the patterns of stars in the night sky were given to them, in most cases thousands of years ago, by cultures that saw in those patterns the figures of their myths and the symbols of their religions. Hercules and Corona Borealis are 2 such patterns, one a depiction of the Greek hero, the other a small semicircular pattern of stars meant to represent a crown. Both are visible in the northern hemisphere of the sky, sitting near each other in the springtime evenings. The constellations themselves have no physical reality. They are not objects in space. They are patterns we have drawn between stars that happen to lie along similar lines of sight from Earth, despite being, in most cases, very different distances away from us. The bright stars of Hercules and Corona Borealis range from approximately 20 light-years away to several hundred light-years. They are not part of any single structure. They simply appear, from our viewpoint, to form recognizable shapes in the sky. What the constellations do provide is a useful reference grid. When astronomers want to communicate where something is in the sky, the easiest way is to say which constellations it appears in. This is the function the constellation names serve in modern astronomy, not as physical descriptions of any actual object, but as labels for regions of the sky. The constellation system is essentially a coordinate scheme, more intuitive than precise but useful for general orientation. The Hercules Corona Borealis Great Wall is located, from our perspective, behind the constellations of Hercules and Corona Borealis. The word behind here means at a great distance. The stars of Hercules are in our galaxy, perhaps a few hundred light-years away, while the Great Wall is approximately 10 billion light-years away. The light from the constellation stars takes only a few hundred years to reach us. The light from the galaxies of the Great Wall takes 10 billion years. In effect, we are looking through the constellation stars to see a structure that is enormously further out, in a region of the universe that existed long before any of the nearby stars or planets were formed. This perspective relationship is worth pausing on. The constellation of Hercules is a small grouping of relatively young stars, none of which is older than perhaps a few 100 million years. The Great Wall, lying in approximately the same direction from our viewpoint, was already arranged in its current form several billion years before any of those stars existed. The stars in the foreground are youthful by cosmic standards. The structure in the background is ancient. To look at Hercules and to know that beyond it lies the Great Wall is to look through the recent past at the deep past, all in the same telescopic view. The actual extent of the Great Wall in the sky is larger than just the regions of Hercules and Corona Borealis. The structure spans from the constellation of Bootes, which lies adjacent to Corona Borealis, through the entire intervening region and into the constellation of Gemini, which is some distance away in the celestial sphere. The total angular extent on the sky is enormous, covering tens of degrees of arc in multiple directions. By comparison, the full moon spans about half a degree. The Great Wall, viewed as a region of the sky, would cover thousands of full moon widths of celestial area if it were directly visible. But it is not directly visible. The individual galaxies that compose the Great Wall are too faint and too distant to be seen by the naked eye, or even by amateur telescopes. Only the very largest professional telescopes, equipped with sensitive instruments capable of detecting very faint light, can identify any individual galaxy at the distances we are talking about. And even those telescopes can only see the brightest of the galaxies within the structure. The full population of galaxies, many of them small, dim, and ordinary by any local standard, is essentially invisible to direct observation. What we have, instead of a direct image, is a statistical pattern. The gamma-ray bursts that occur within the galaxies of the Great Wall are detected one at a time over many years by satellite telescopes that scan the sky for these brief events. Each burst is plotted on a map. Over time, the map builds up. The clustering pattern emerges. The structure becomes visible, not as a coherent image but as a region of higher density and a map of explosions. The constellations in this story are the foreground through which we look. They are nearby, familiar, and well named. Behind them, 10 billion light-years deeper into space and time, lies a structure they do not contain and to which they have no real connection. The structure is hidden by distance and by the limits of our vision, but it is not hidden from inference. We know it is there because the data keeps telling us so. It is worth lingering for a section on what gamma-ray bursts actually are. They are central to the story of the Great Wall, and they are also among the strangest and most extreme phenomena that astronomers have ever identified. Understanding them, even approximately, makes the rest of the story easier to follow. Gamma rays are a form of electromagnetic radiation, like visible light, but with much shorter wavelengths and much higher energies. The light you see with your eyes corresponds to wavelengths of approximately 400 to 700 nanometers. Gamma rays have wavelengths shorter than about 1/10 of a nanometer, which means each individual gamma ray photon carries far more energy than a photon of visible light, often millions or even billions of times more. They are produced naturally in various extreme astrophysical processes, including nuclear reactions, particle decays, and the kind of catastrophic events we are about to describe. A gamma ray burst is, as the name suggests, a burst of gamma rays. What distinguishes a burst from other gamma-ray sources is its brevity and its extreme intensity. A typical burst lasts from a fraction of a second to a few minutes. During that time, it emits an amount of energy that is comparable to what the Sun will emit over its entire 10 billion year lifetime. The energy is concentrated into a narrow region of space and a brief moment of time, which produces an apparent brightness that, for those brief moments, can exceed the combined brightness of every other source in the observable universe. The phenomenon was discovered, oddly enough, by accident. In the late 1960s, the United States launched a series of satellites called Vela, designed to detect the signatures of nuclear weapons tests in space. The Vela satellites detected gamma rays. They were intended to distinguish between gamma rays from nuclear explosions on Earth and gamma rays from natural cosmic sources. What they actually found was something neither category had predicted: short, intense bursts of gamma rays coming from random directions in space with no apparent connection to any human activity or any known astronomical source. The discovery was kept classified for several years before being released in 1973. From that moment on, gamma-ray bursts have been one of the central puzzles of high-energy astrophysics. The puzzle was not solved quickly. For decades it was unclear what gamma-ray bursts even were, where they came from, or how they were produced. They appeared randomly across the sky, with no obvious clustering. They were so brief that follow-up observations were difficult. They were so bright that they had to be either very close, perhaps within our own galaxy, or very far away and incredibly powerful. The distance question was finally resolved in the late 1990s, when astronomers identified the host galaxies of several bursts and measured their distances. The galaxies were billions of light-years away. This meant the bursts were occurring at cosmological distances, and that they had to be among the most luminous events ever observed in the universe. The current understanding is that gamma-ray bursts come in two main types, distinguished by their durations. Long bursts, lasting more than approximately 2 seconds, are produced when very massive stars, perhaps 30 or more times the mass of the Sun, collapse at the end of their lives. The collapse forms a black hole, and the surrounding stellar material is squeezed into an accretion disk that produces narrow jets of matter moving at nearly the speed of light. The jets, if they happen to be pointed approximately toward Earth, produce the gamma-ray burst we observe. The probability of any specific burst being aimed at us is low. Most bursts go in other directions and are never detected, but the universe contains so many massive stars that bursts are observed at a rate of approximately 1 per day from somewhere in the observable universe. Short bursts, lasting less than approximately 2 seconds, are produced by a different mechanism. The most likely explanation involves the collision of two neutron stars in a binary system, or possibly the collision of a neutron star with a black hole. The collision releases enormous energy in a brief moment, including gamma rays and gravitational waves. The detection of gravitational waves from such collisions, beginning in 2017, has confirmed the basic picture and made short gamma-ray bursts among the best understood violent events in the universe. For the purposes of the Great Wall story, what matters is that gamma-ray bursts are visible across most of the observable universe. They are bright enough to be detected at distances where ordinary galaxies become invisible. They mark the locations of star formation and stellar death, which means they trace the underlying distribution of matter. By mapping where bursts occur, astronomers can map where galaxies are, even when the galaxies themselves are too faint to be seen directly. The Great Wall was found by looking at lighthouses. Each burst is a lighthouse briefly visible that points to a galaxy. The pattern of all those lighthouses, accumulated over years of observation, is what the data ultimately revealed. There is a habit of mind in astronomy that takes some practice to acquire. It involves accepting that most of what we know about the universe has not been seen in any direct sense. The objects are too far away, the structures are too large, the events are too brief, the light is too faint or too red or too obscured by dust. The actual experience of looking at the universe with a telescope is, for the most part, the experience of looking at faint smudges, statistical patterns, and indirect signatures of things that cannot be observed any other way. The map of the Hercules Corona Borealis Great Wall is a particularly extreme example of this. There is no photograph of the wall. There is no telescope image showing a glowing band of galaxies stretched across the sky. The light from the individual galaxies that compose the structure is far too faint, and the structure as a whole is far too large to be captured in any single image or any single observation. What there is instead is a database of gamma-ray burst positions and redshifts accumulated over decades, plotted on a map of the celestial sphere, and analysed for statistical clustering. The structure exists in the analysis. It is real in the sense that the pattern in the data is real and reproducible, but it does not exist as an image, and it never will. This way of knowing is unfamiliar to most people who are used to thinking of knowledge as visual. The map of the cosmic web at very large scales is not knowledge of this kind. It is knowledge of a different kind, statistical, inferential, dependent on long chains of measurement and analysis that no single observation could replace. Each piece of the chain is checked, verified, and refined. The result is robust, in the sense that many independent lines of evidence support it. But it is not visual in the immediate intuitive way that a photograph of the moon is visual. The same is true of most of modern cosmology. Dark matter, which makes up the great majority of the matter in the universe, has never been directly observed. We know it exists because of its gravitational effects on the motion of galaxies and on the bending of light from more distant objects. The Big Bang itself has not been observed in any direct sense. We know it occurred because of the cosmic microwave background radiation, the abundance of various elements in the universe, and the expansion of space measured through the redshifts of distant galaxies. The cosmological framework that underlies our understanding of everything, including the Great Wall, is built from many pieces of evidence, almost all of them indirect. The advantage of this approach is that it allows us to study things that cannot be studied any other way. The disadvantage is that it requires patience with the limits of what can be known directly. When you read about the Great Wall, you are not reading about something that has been seen. You're reading about something that has been inferred. The inference is careful, based on data, and tested by multiple research groups using different methods, but it is still an inference. And the structure could, in principle, turn out to be wrong, a statistical fluke, a systematic error in the data, an artifact of how gamma-ray bursts happen to be distributed for reasons that have nothing to do with underlying matter distribution. This is why scientific publications about the Great Wall typically include extensive discussion of statistical methods, uncertainty estimates, and possible alternative explanations. The authors are aware that they are making claims about something they have not seen. They are careful to show that the evidence supports the claim, that the clustering is statistically significant, that it appears in multiple independent datasets, and that it cannot easily be explained by selection effects or sampling biases. The papers are long and technical. They are designed to convince other scientists, who are themselves trained to be skeptical of claims about very large or very distant objects. The result, after more than a decade of analysis, is a structure that most cosmologists accept as probably real, while still acknowledging the possibility that future data might revise or refute the conclusion. The Great Wall has not been definitively proven. It has been repeatedly tested, with results that consistently support its existence, but the standards of evidence in this kind of work are not the same as the standards for an object you can simply look at through a telescope. The acceptance is conditional. It depends on the evidence continuing to hold up. There is something fitting in this. A structure so large that no single image could ever contain it is also a structure so large that no single observation could ever fully confirm it. It exists in the accumulated weight of many observations, many analyses, many independent confirmations. It is a structure that has to be assembled, in our understanding, the same way it was assembled in space, slowly over time from many separate pieces. The paper that announced the discovery of the Hercules Corona Borealis Great Wall was submitted to the journal Astronomy and Astrophysics on August 18, 2014. It was accepted for publication after revision and appeared in November 2015. The authors were Istvan Horvath, Jon Hakala and Zsolt Bagoli, working together on a project that had begun several years earlier with the more general goal of using gamma-ray bursts to map the large-scale structure of the universe. The paper itself is relatively short by the standards of major astronomical papers, only about a dozen pages in its published form. The title is direct. New data support the existence of the Hercules Corona Borealis Great Wall. The abstract describes the analysis of an updated catalogue of gamma-ray bursts and concludes that the clustering of bursts in a particular region of the sky, at redshifts between approximately 1.6 and 2.1, was statistically significant. The clustering, the authors argued, indicated the presence of a very large coherent structure in the underlying distribution of matter. The paper built on earlier work by the same team. Horvath and his colleagues had been studying the distribution of gamma-ray bursts for years, looking for patterns that might reveal information about the large-scale structure of the universe. In a paper published in 2014, They had identified an apparent overdensity of bursts in the region that would eventually be called the Great Wall. The 2015 paper used a larger dataset and applied more rigorous statistical tests, confirming the result and refining the estimate of the structure's size. The methodology was straightforward in concept, even if difficult in execution. The team compiled a catalogue of all known gamma-ray bursts with measured redshifts, that is, all bursts for which the distance from Earth had been determined. They divided this catalogue into bins by redshift, separating bursts that occurred at different distances. They then examined the angular distribution of bursts in each redshift bin, that is, how the bursts were distributed across the sky. If the distribution were uniform, as the cosmological principle predicts, then bursts at any given redshift should be spread roughly evenly across the sky. What the team found was that in certain redshift bins, the distribution was not uniform. There was a clear overdensity of bursts in one direction, specifically in the region of Hercules and Corona Borealis at redshifts of approximately 1.6 to 2.1. The overdensity was substantial. It corresponded to roughly twice the expected number of bursts in that region, given the total number of bursts at those redshifts in the dataset. The probability that this overdensity could have arisen by chance, given a uniform underlying distribution, was very low. Less than 1% according to the statistical tests applied by the team. The interpretation was that the overdensity of bursts traced an underlying overdensity of matter. Bursts occur in galaxies, and the rate of bursts in any region of space depends on the number of galaxies and the rate of star formation in those galaxies. If there are more bursts in a region of sky, the simplest explanation is that there are more galaxies there. The clustering of bursts therefore indicates a clustering of galaxies, which is to say, a large coherent structure in the cosmic web. The size of the structure could be estimated from the angular extent of the burst overdensity and the redshifts of the contributing bursts. The result was an extent of approximately 10 billion light-years in the longest direction, substantially larger than any other known structure. The team noted in the paper that this size was difficult to reconcile with standard cosmological models, which predict that structures should not grow beyond approximately 1.2 billion light-years in the time available since the Big Bang. The response to the paper was substantial. Other astronomers began to examine the data themselves, applying their own statistical tests, looking for alternative explanations, and checking whether the clustering could be explained by selection effects in the gamma-ray burst sample. The general conclusion of these follow-up analyses was that the clustering was robust. It could not easily be explained away. The structure appeared in the data persistently, across multiple methods of analysis and multiple subsets of the burst catalogue. What changed in 2014, then, was not so much the discovery of a new object as the elevation of an existing pattern in the data to the status of a recognized cosmic structure. The clustering had been visible in earlier datasets, but it had not been definitively identified as a coherent feature. The 2014 paper, supported by the 2015 confirmation, established the Great Wall as a real astronomical entity. It became, from that point forward, an object that subsequent researchers would have to engage with, either by proposing better explanations of the data, by extending the measurements, or by accepting it as a feature of the universe that the standard cosmological model now had to account for. The paper has been cited hundreds of times since its publication. The discussion it initiated has continued for more than a decade. It is one of the most consequential cosmological papers of the 2000s, and its conclusions remain a subject of active research. It is impossible to understand the Great Wall without understanding redshift. The concept is central to modern cosmology, central to how we know that the universe is expanding, and central to how we measure distances at the scales we are talking about here. It is also a concept that takes a moment to absorb, because it depends on a physical effect that does not have an obvious analogue in everyday experience. Light, like all forms of electromagnetic radiation, has a wavelength. Different wavelengths correspond to different colours, in the case of visible light, or to different parts of the electromagnetic spectrum more broadly. When a source of light is moving relative to an observer, the wavelengths of the light are shifted from the values they would have if the source was stationary. If the source is moving toward the observer, the wavelengths are compressed and the light is shifted toward the shorter, bluer end of the spectrum, a blue shift. If the source is moving away from the observer, the wavelengths are stretched and the light is shifted toward the longer, redder end of the spectrum, a red shift. This effect is familiar from sound. The pitch of a passing ambulance siren is higher when the ambulance is approaching and lower when it is receding. The same principle applies to light. though the speeds required to produce a noticeable effect on visible light are extraordinarily high. For everyday objects moving at everyday speeds, the wavelength shift is far too small to detect. For galaxies in the universe, however, the effect is large. When astronomers measure the spectra of distant galaxies, the patterns of light at different wavelengths, they find that the patterns are systematically shifted toward the one. The shift increases with distance. The farther away a galaxy is, the more its light is redshifted. This pattern, discovered in the early 20th century by Edwin Hubble and others, is the basis for the conclusion that the universe is expanding. The space between galaxies is stretching, and the wavelengths of light travelling through that space are stretched along with it. The amount of redshift is described by a number, conventionally denoted by the letter Z. A galaxy with Z equals 0 has no redshift. A galaxy with Z equals 1 has its light wavelength stretched to twice their original values. The galaxy is moving away from us at a substantial fraction of the speed of light. A galaxy with Z equals 2 has wavelengths stretched to 3 times their original values. Higher redshifts correspond to greater distances and to earlier moments in cosmic history, because the light has been travelling longer to reach us. The Hercules Corona Borealis Great Wall, as identified in the original Horvath paper, is located at redshifts between approximately 1.6 and 2.1. The more recent re-examination by Hackler and colleagues suggests it may extend across an even wider range, from approximately 0.33 to 2.43. These redshifts correspond to distances of approximately 5 to 11 billion light-years from Earth, with the central concentration at around 10 billion light-years. The use of redshift to measure distance involves some subtleties. The relationship between redshift and distance is not strictly linear at large redshifts, because the expansion of the universe has not been constant over its history. Modern cosmologists use a model called lambda c dm, which includes dark energy and dark matter, and is consistent with a wide range of observations. Under this model, the redshift-distance relationship is well defined, and the distances to objects with measured redshifts can be calculated to reasonable precision. For the Great Wall, the redshift measurements come from the host galaxies of the gamma-ray bursts that compose the structure. Each burst, once its position has been identified, is matched with a galaxy in that location, and the spectrum of the galaxy is measured to determine its redshift. The redshifts of all the bursts in the wall, taken together, define the depth and extent of the structure. One important consequence of the redshift-distance relationship is that, at the redshifts of the Great Wall, we are looking deep into the past. Light that left the wall at Z equals 2 has been travelling for about 10 billion years. This means we are seeing the structure as it was 10 billion years ago. The galaxies that compose the wall, as we see them, are young galaxies in the early stages of their development. They have continued to evolve over the 10 billion years between then and now. The current state of the wall, what it looks like at the present moment, 10 billion years after the light we now observe was emitted, is something we cannot directly observe. We can only see the past. This is true of everything in astronomy, but the timescales involved with the Great Wall make the point particularly vivid. The structure exists. It existed when the light left. It almost certainly still exists in some form. But we are looking at a snapshot, taken many billions of years ago, of what has continued to evolve in the time since the snapshot was made. The name Great Wall suggests something specific. A wall is flat. A wall has 2 extended dimensions and 1 short one. A wall is a recognizable kind of structure, with clear edges and a clear orientation. When astronomers chose to call the Hercules Corona Borealis structure a wall, they were making a claim about its shape, that it is more flat than spherical, more extended than thick, more sheet-like than cloud-like. The classification rests on detailed measurements of the structure's 3-dimensional extent. The Great Wall is approximately 10 billion light-years in its longest dimension. It is roughly 7 billion light-years across in the perpendicular direction, and it is approximately 1 billion light-years thick in the 3rd dimension. These 3 numbers give a shape that is substantially more extended in 2 dimensions than in the 3rd, the defining feature of a wall. The reason structures of this shape exist in the universe is the same reason any structure exists. The cosmic web is not isotropic. It does not produce spherical blobs of matter scattered randomly across space. It produces a network of filaments and sheets, with matter concentrated along lines and surfaces rather than at random points. The geometry of the network is a consequence of how gravity operates on the initial density fluctuations from which structure formed. Slightly overdense regions in the early universe collapsed first in the direction of their highest density, producing pancake-like sheets. The sheets then fragmented further, with matter flowing along their planes toward higher density regions where filaments formed. The filaments in turn fed into clusters at their intersections. The whole process produces a hierarchical structure with sheets, filaments, and clusters at different scales. The Hercules Corona Borealis Great Wall in this scheme would be classified as a sheet, or more precisely, as a complex of sheets and filaments that together form a roughly wall-like configuration over the relevant scales. It is not a single uniform structure. Detailed mapping reveals internal organization, denser regions where multiple filaments converge, more diffuse regions in between, voids of various sizes within the larger structure. But viewed at the largest scale, the overall shape is more wall-like than anything else. Other terms have been used at various points in the literature. Some papers refer to the structure as a supercluster complex, emphasizing the fact that it contains many superclusters embedded within it. Others use filament when discussing the longest direction of extension. The choice of term is partly a matter of emphasis, and partly a matter of which aspect of the structure the author wishes to highlight. Great Wall has prevailed in popular usage because it is shortened to descriptive and evocative. The question of why the structure has the shape it does is connected to the question of how it formed. The standard model of structure formation predicts that walls and filaments should arise naturally as the universe evolves. The detailed predictions involve complex simulations that follow the gravitational collapse of matter, from the small initial fluctuations to the structures we see today. These simulations reproduce the general statistical properties of the cosmic web reasonably well: the distribution of filament lengths, the density of voids, the masses of galaxy clusters. But they have difficulty reproducing structures as large as the Great Wall. The simulations tend to produce many smaller structures and fewer large ones. The Great Wall at its full extent sits at or beyond the upper limit of what the simulations are able to generate. This is part of what makes the structure so interesting. It is not just an unusually large object. It is an object that may indicate the existence of physical processes or initial conditions that the standard simulations do not capture. If the simulations underpredict the largest structures, then something about how the simulations represent the early universe, or about how gravity operates at the largest scales, may be incomplete. The alternative is that the simulations are essentially correct, and the Great Wall is a statistical fluke, an unusually large structure that, while improbable, is not actually impossible given enough universe to search through. Distinguishing between these two possibilities is difficult. It requires either better data on large structures, better simulations of the cosmic web, or better theoretical understanding of how structures form. All three are active areas of research, but progress is slow. The relevant scales are enormous, the relevant processes are subtle, and the data is sparse at the distances involved. In the meantime, the Great Wall sits in the data, classified as a wall by virtue of its shape, classified as a problem by virtue of its size. It continues to exist whether or not we have a complete explanation for why. The universe is under no obligation to organize itself around the predictions of our models. Sometimes it organizes itself in ways that the models did not anticipate, and the models have to be revised. That may be the eventual outcome here, or it may turn out that the standard model can accommodate the Great Wall after all, with modifications that have not yet been worked out. Either way, the structure is real until shown otherwise, and the conversation about it continues. A wall of this size is not made of nothing. It is made of galaxies. Enormous numbers of galaxies, organized into groups and clusters, with the clusters connected by smaller filaments and the whole assembly arranged into the larger structure that we identify as the wall. To understand what the Great Wall actually consists of, we have to think for a moment about its components, the individual building blocks that, taken together, produce the largest object in the known universe. A galaxy is a self-contained system of stars, gas, dust, and dark matter, held together by gravity. Galaxies vary enormously in size and composition. The smallest dwarf galaxies contain perhaps a few million stars and are only a few thousand light-years across. The largest galaxies, giant elliptical galaxies found at the centerpoles of major clusters, can contain trillions of stars and span hundreds of thousands of light-years. The Milky Way, our own galaxy, is somewhere in between, with approximately 200 billion stars and a diameter of about 100,000 light-years. Galaxies are the basic units of the visible universe at large scales. Almost every star in the universe is part of one. Galaxies, in turn, are often grouped together. The Milky Way is part of a small collection called the Local Group, which contains about 30 galaxies, including our own, Andromeda, and various smaller satellite galaxies. The Local Group is, in turn, part of the Virgo supercluster, a much larger collection of approximately 100 galaxy groups. The Virgo supercluster is, in turn, part of the Laniakea supercluster, an even larger structure containing approximately 100,000 galaxies. Each step up the hierarchy involves a larger collection, more loosely bound, with internal structure that includes the smaller collections from which it is built. The Hercules Corona Borealis Great Wall sits at the top of this hierarchy. It contains many superclusters, each containing many clusters, each containing many groups, each containing many individual galaxies. Estimates of the total number of galaxies within the structure are difficult, because the structure has not been mapped galaxy by galaxy in any comprehensive way. The mapping has been done through gamma ray bursts, which trace only a small fraction of the total galaxy population. But statistical estimates, based on the density of matter implied by the burst clustering, and on the typical galaxy density in similar structures, suggest that the total number of galaxies within the wall is in the range of many hundreds of thousands or possibly millions. The galaxies are not, of course, uniformly distributed within the wall. They are concentrated along filaments, with denser concentrations where filaments meet and less dense regions in between. The structure, viewed at sufficient resolution, would look something like a tangled network of bright strings, with knots at the intersections and voids in between. The voids within the structure are themselves substantial, regions tens or hundreds of millions of light-years across where galaxy density is low, compared to the surrounding filaments. The wall is therefore not a solid mass of galaxies, but a sparse network. The total amount of space within the boundaries of the structure is enormous, but the fraction of that space actually occupied by galaxies is quite small. Most of the volume within the wall is, in a sense, empty, filled only with the very low density of intergalactic gas and dark matter that permeates space at large scales. The galaxies are the bright spots in the network. The dark spaces between them constitute the great majority of the volume. The light from all these galaxies taken together would be substantial if it could be combined into a single image. But the galaxies are spread across 10 billion light-years of distance, and the light has been travelling for 10 billion years to reach us. The arriving light is spread across the entire sky, concentrated in the direction of Hercules and Corona Borealis, but extending across multiple constellations. No telescope ever built could combine all this light into a single coherent image. We see only fragments. We see the bright galaxies in our maps, the gamma ray bursts in our catalogues, the statistical patterns in our analyses. The wall as a whole is something we can describe but not see. What the description tells us is that the structure is a community of galaxies, organized at multiple scales, bound by the gravitational influence of dark matter, illuminated by the brief lives of stars in its constituent systems. Each galaxy within the wall has its own internal life, its own stars forming and dying, its own central black hole, its own history of mergers and interactions with neighbouring galaxies. Each contains, presumably, planets and possibly the conditions for life. Each is, in some sense, a world of its own, embedded within a much larger world that is itself embedded within the wall, which is embedded within the cosmic web, which is embedded within the observable universe. The hierarchy continues outward indefinitely. The Great Wall is a single level of organisation within this hierarchy, one level that happens to be the largest yet identified. To say that the Great Wall is 10 billion light-years across is to invoke a number that the mind cannot fully absorb. The number is real. The number is measured. The number is reproducible by independent methods, but the number does not connect to anything in human experience, and it has to be approached carefully if it is to mean anything at all. A light-year is the distance light travels in a year. Light moves at 300,000 kilometers per second, a speed that in everyday terms would take you around the Earth approximately 7.5 times in a single second. Over the course of a full year, light covers about 9.5 trillion kilometers. This is 1 light-year. The nearest star to the Sun, Proxima Centauri, is approximately 4.25 light-years away. The light from Proxima Centauri that reaches your eyes tonight, if you happen to be in the southern hemisphere where it is visible, left the star a little over 4 years ago. Now multiply by 10 billion. The total distance is 95 sextillion kilometers. The number has so many zeros that writing them out is not particularly useful. The unit of kilometers, which works well for distances on Earth, has long since ceased to be helpful at this scale. Even the light year, which works for distances within and between galaxies, begins to strain at the very largest cosmic distances. Astronomers tend to use the megaparsec or gigaparsec instead, units defined for these enormous spans. 1 gigaparsec is approximately 3.26 billion light-years. The Great Wall is therefore about 3 gigaparsecs across. The numbers can be manipulated. The arithmetic is straightforward. But none of this produces an intuition for the distance. To produce an intuition, you have to think in terms of time rather than space. The light that left the far edge of the wall began its journey at a moment when the universe was approximately 3 to 4 billion years old. The Sun did not exist. The Earth did not exist. The atoms that would eventually form your body had probably been forged in stars that themselves did not exist. The early life forms that would eventually evolve into all life on Earth, including the lineage that produced you, had not yet been imagined by any mechanism in the universe, because the conditions for them had not yet arisen. The light started its journey across an enormous distance through an expanding universe at a moment when essentially nothing of what you know existed. The light travelled, galaxies formed and merged, stars were born and died. The chemical elements that would eventually become planets accumulated in the disks of newly forming solar systems. Around one particular star in one particular galaxy, a small rocky planet formed. The planet cooled, oceans appeared on its surface, single-celled organisms emerged in those oceans. Over the course of billions of years, those organisms evolved into more complex forms, and then into multicellular creatures, and then into the great variety of life forms that have populated the Earth across its long history. The light kept travelling. It crossed regions of space that were themselves expanding, stretching the wavelengths of the light along the way. It did not change direction. It did not lose energy except through the cosmological redshift. It simply continued, second by second, year by year, toward a destination it could not know. The destination was a small planet, on which, after billions of years of evolution, a species had emerged that built instruments capable of detecting gamma rays from space. The species pointed its instruments at the sky. The instruments registered the arriving light. The data was recorded, analysed, plotted on maps of the celestial sphere. The pattern that the light revealed, when combined with the patterns of light from many other gamma-ray bursts, indicated the presence of a large structure in a particular region of the sky. The light that started its journey at the far edge of the wall, 10 billion years before the species existed that would eventually detect it, completed its journey by being absorbed into the detector of a satellite in orbit around Earth. The journey, considered as an event, lasted longer than the entire history of life on Earth. The destination, considered as a recipient, did not exist for most of the journey. The connection between the source and the receiver was made possible only by the fact that light persists indefinitely in space, that nothing stops it from travelling, that the universe is transparent to the kind of light we are talking about across these enormous distances. There is something humbling and something settling in this. The light was sent before anything was ready to receive it. The receiver evolved into existence in time to catch a small fraction of what had been sent. The fraction that we caught is small. The pattern we constructed from that fraction is what we have. The rest continues outward, into a future no one will live to see, carrying information no one will ever assemble. It seems strange, on first reflection, that the largest known object in the universe was not identified until 2014. Astronomy is a very old field. Telescopes have been pointed at the sky for 400 years. Surveys of galaxies have been conducted for more than a century. The cosmic microwave background was mapped in detail starting in the 1990s. The cosmic web has been studied through galaxy redshift surveys for decades. Why did such a vast structure escape detection for so long? The answer, when it is fully laid out, makes the late discovery seem not strange but inevitable. The Great Wall was hidden by exactly the combination of factors that would be expected to hide it. It is too distant to be seen with ordinary galaxy surveys, which depend on direct observation of galaxies and which become incomplete at the distances involved. It is too large to be apparent in any single field of view, which means that even very sensitive observations of small patches of sky could not have revealed it. and it is too sparse, in the sense that its galaxies are spread across an enormous volume, to be obvious in any visualization that does not aggregate data from across the entire celestial sphere. The history of cosmological surveys helps explain the situation. The first major surveys of galaxy positions began in the 1970s and 1980s, with the Center for Astrophysics Redshift Survey and various other early projects. These surveys catalogued thousands of galaxies, primarily relatively nearby ones, and revealed the first hints of the cosmic web, the sense that galaxies were not uniformly distributed, but were arranged in patterns. In the 1990s and 2000s, larger surveys followed, including the 2-degree field galaxy redshift survey and the Sloan Digital Sky Survey, which catalogued hundreds of thousands and then millions of galaxies. These surveys produced detailed maps of the cosmic web at relatively low redshifts, generally less than 0.5, corresponding to distances of less than about 5 billion light-years. They revealed many of the structures we now know up, including the Sloan Great Wall, which was the largest known structure until the Hercules Corona Borealis Great Wall was identified. What the galaxy surveys could not do was extend their reach to redshifts much greater than about 1. Beyond that distance, galaxies become too faint to be detected efficiently by survey instruments. Specialized observations can identify individual high redshift galaxies, but comprehensive mapping at high redshifts has not been possible with the available technology. This means that the region of the universe where the Great Wall is located, at redshifts of approximately 1.6 to 2.1, was not accessible to ordinary survey methods. Whatever was out there would have to be revealed by other means. Gamma-ray bursts provided the other means. They are visible at much higher redshifts than ordinary galaxies, and they can be detected efficiently by satellite instruments that survey the entire sky continuously. The accumulation of burst data over the course of decades, beginning seriously in the 1990s with major improvements through the launches of the Swift satellite in 2004 and the Fermi satellite in 2008, gradually built up a catalogue large enough that statistical patterns in the burst distribution could be identified. The Great Wall emerged from this catalogue as the analysis methods improved and the dataset grew. There is a more general point in this. The cosmic web has been mapped at various scales by various methods. At small distances, we use galaxy surveys. At medium distances, we use quasar surveys, in which the bright nuclei of distant galaxies serve as markers for the underlying matter distribution. At the very largest distances, we use gamma-ray bursts, because these are essentially the only objects bright enough to be detected at the relevant redshifts. Each method has its strengths and limitations. Each reveals different aspects of the underlying structure. The Great Wall happens to be visible primarily to the gamma-ray burst method, which is why it was not detected until that method had matured. This means that other very large structures may exist that have not yet been identified. The gamma-ray burst catalogue is still growing. New analyses continue to be conducted. Other methods, including future surveys of the cosmic microwave background and other traces of large-scale structure, may reveal additional features that have so far gone unnoticed. The Great Wall is the largest known structure as of the time of this recording, but the word known is doing significant work in that statement. There may be larger structures in the universe that have not been mapped because the methods to map them have not yet been developed or applied. The history of astronomy is, in many ways, the history of detecting things that were already there. The universe contains everything it contains, regardless of what we have managed to observe. What changes is our ability to see. The 2014 discovery of the Great Wall did not put a structure into space. The structure was already there and had been there for billions of years. The discovery put the structure into our awareness. It became, in 2014, something that we knew about. Before then, it was simply something that existed. At the heart of modern cosmology lies an idea so basic that it is rarely discussed explicitly. The idea is called the cosmological principle, and it states that the universe, viewed at sufficiently large scales, is essentially the same everywhere and in every direction. There are no preferred locations, there are no preferred directions. Whatever is true in one part of the universe is true, on average, in every other part. This is a strong claim. It is also, in some sense, an assumption rather than a discovery. We cannot directly verify that the universe looks the same in regions we cannot observe. We can only verify that the observable portion of the universe, the volume of space from which light has had time to reach us, appears to satisfy the principle reasonably well at very large scales. The assumption that this pattern continues beyond the observable horizon is just that, an assumption. It is a useful assumption, supported by the symmetry it implies and by various theoretical considerations, but it cannot be tested in any direct way. The cosmological principle has two components, usually stated together. The first is homogeneity, which means that the universe has the same average density of matter and the same average properties everywhere. The second is isotropy, which means that the universe looks the same in every direction. These are slightly different claims, and they can in principle be tested separately, but they are usually treated together because they are both natural consequences of the same underlying symmetry. The cosmological principle is supported by a variety of observations. The cosmic microwave background, the faint radiation left over from the early universe, is remarkably uniform across the sky. Its temperature varies by only about 1 part in 100,000 between different directions after subtracting out the effects of the Earth's motion through space. The expansion of the universe, as measured by the redshifts of distant galaxies, appears to proceed at the same rate in all directions, again after the appropriate corrections. The large-scale distribution of galaxies, averaged over sufficiently large volumes, appears statistically uniform. But the support is not perfect. The cosmic microwave background has known anomalies, small features that do not quite fit the expected statistical patterns. The expansion rate of the universe, as measured by different methods, gives slightly different values, which has produced the so-called Hubble tension that has occupied cosmologists for years. And the existence of very large structures like the Great Wall raises questions about whether the universe really is as homogeneous as the principle requires. The relevance of the Great Wall to the cosmological principle is that if the principle is true, structures of this size should not exist. The principle does not forbid the existence of any particular structure outright. It says instead that structures should average out at large scales, that the irregularities should be relatively small compared to the overall uniformity. The maximum size of a structure that is consistent with the principle has been estimated, based on the rate at which structures grow under gravitational attraction in an expanding universe, at approximately 1.2 billion light-years. Anything larger than this calls the principle into question. The Great Wall is, by current estimates, about 10 times larger than this limit. It is roughly the size that would require the cosmological principle to be substantially revised. The existence of the wall therefore raises a serious theoretical question. Is the cosmological principle wrong? Or is the Great Wall a statistical fluke, an unusually large structure that, while improbable, does not actually violate the principle when interpreted correctly? This is the question that has occupied cosmologists since the Great Wall was discovered. Different researchers have reached different conclusions. Some argue that the structure is real and indicates a genuine violation of the cosmological principle at large scales. Others argue that the structure is real, but that the principle can accommodate it through statistical interpretation, that very large structures can exist as rare events even in a universe that is on average homogeneous. Still others question whether the structure is fully real, or whether parts of it might be artifacts of how gamma-ray bursts are detected and catalogued. The cosmological principle is too useful to abandon without strong reasons. It underlies essentially all of modern cosmology. The mathematics of the expansion of the universe, the calculations of how structure forms, the interpretations of the cosmic microwave background, all of these depend on the assumption of homogeneity and isotropy at large scales. Abandoning the principle would require rebuilding a substantial portion of the cosmological framework, which would be a major undertaking with consequences for many other parts of the field. So the principle is being defended while the Great Wall is being studied. The two activities are not in opposition. The defenders of the principle are interested in whether the wall is real, and if so, whether it can be accommodated within the existing framework. The studiers of the wall are interested in whether the principle can fully account for what they are observing. The two communities overlap substantially. The conversation continues and the answer is not yet clear. The specific theoretical limit that the Great Wall appears to violate comes from calculations of how quickly gravitational structures can grow in an expanding universe. The calculations involve a combination of general relativity, statistical mechanics, and the specific parameters of the cosmological model, the density of matter, the rate of expansion, the contribution of dark energy. The result is a number called the cosmological correlation length, which describes the largest scale at which density fluctuations in the universe are expected to be substantially coherent. The current value of the correlation length is approximately 370 megaparsecs, which corresponds to about 1.2 billion light-years. This means that in the standard cosmological model, regions of the universe separated by more than about 1.2 billion light-years should have essentially independent density fluctuations. A region that happens to be denser than average can correlate with its neighbours over scales of up to about 1 billion light-years, but beyond that scale, the correlations should fade away. Structures larger than the correlation length should not form, because the gravitational dynamics that produces structures cannot operate coherently across distances that exceed it. The Great Wall, at 10 billion light-years, is about 10 times the correlation length. The recent measurements that suggest 15 billion light-years make the discrepancy even worse. By any reasonable interpretation of the standard model, structures of this size should not exist. They cannot have formed by the gravitational growth of initial density fluctuations within the time available since the Big Bang. The structures should not be there, but the structure is there. This is the puzzle. The standard responses to this kind of theoretical conflict take several forms. The first is to question the data, to ask whether the structure is really as large as it appears to be, or whether some aspect of the measurement might be inflating its apparent size. This is a reasonable line of inquiry, and it has been pursued vigorously. Various analyses have looked for systematic effects in the gamma-ray burst data that could produce a false impression of clustering. So far, no such effect has been definitively identified. The clustering survives every test that has been applied to it. The second response is to question the theoretical limit, to ask whether the calculation of the correlation length might be missing something, or whether modifications to the standard model could produce a larger limit. This line of inquiry has also been pursued. Various extensions of the standard model, including modifications to dark matter properties, alternative theories of gravity, and exotic early universe scenarios, have been considered as possible ways to accommodate the wall. Some of these extensions can, in principle, produce structures of the required size, but they introduce their own theoretical complications and have not been definitively supported by other observations. The third response is to accept that very large structures can exist as rare statistical fluctuations even in a universe whose typical structure scale is much smaller. This is sometimes called the rare event interpretation. Under this view, the Great Wall is not impossible, it is just very improbable. If you look at enough of the universe, eventually you find structures that are statistical outliers, much larger than the typical scale. The cosmological principle in this interpretation is preserved on average even though specific regions can have unusual features. The rare event interpretation has some appeal, but also some difficulties. The main difficulty is calculating just how improbable the Great Wall is, given the standard model. The calculation depends on how much of the universe one is searching through, and on the statistical distribution of structure sizes that the standard model predicts. Reasonable estimates suggest that finding a structure as large as the Great Wall in the observable universe is improbable at the level of less than 1%, possibly much less. This is improbable enough to be suspicious, but not so improbable as to be definitively impossible. There is no consensus among cosmologists about which of these responses is correct. The data continues to accumulate. The theoretical analyses continue. Different research groups maintain different positions, with the most cautious accepting the structure as real while remaining agnostic about its implications, and the more theoretically committed proposing specific modifications to the standard model that could accommodate it. What is clear is that the Great Wall has become a kind of test case for modern cosmology. Whatever turns out to be the resolution, whether the structure is a statistical fluke, a sign of new physics, or something else entirely, the resolution will tell us something important about how the universe works at the largest scales. The wall is not just a curious object, it is a probe of cosmological theory applied to the data, returning a result that the theory has so far been unable to explain comfortably. The result may eventually be incorporated into a refined theory, or it may force a substantial revision of the existing framework. Either outcome would be a major development in cosmology, with implications that extend well beyond the specific question of how a single structure came to exist. To understand more deeply why the Great Wall is theoretically problematic, it helps to understand the theory of cosmic inflation. Inflation is the proposal, first developed in the early 1980s by Alan Guth and others, that the universe underwent a period of extremely rapid expansion in its very early history, a tiny fraction of a second after the Big Bang. During this period, the universe is supposed to have expanded by a factor of at least 10 to the 26th power in less than 10 to the minus 32nd power seconds. The expansion was driven by a hypothetical field whose properties caused the rate of expansion to accelerate exponentially. Inflation was proposed to solve several specific problems with the original Big Bang model. One of these problems was the horizon problem, the observation that the cosmic microwave background appears remarkably uniform across the sky, even in regions that should never have been in causal contact with each other under the standard Big Bang scenario. How could distant regions of the universe come to have the same temperature, to better than 1 part in 100,000, if they had never had the chance to exchange energy or information? Inflation solves the horizon problem by proposing that the regions were once close together, in causal contact, before being driven apart by the inflationary expansion. The uniformity is a memory of the time before inflation, preserved across the much larger distances that resulted from it. Another problem inflation solved was the flatness problem, the observation that the geometry of the universe appears remarkably flat, which requires its total density to be remarkably close to a specific critical value. Without inflation, there is no reason for the universe to have this particular density. With inflation, the rapid expansion drives the geometry toward flatness, regardless of the initial conditions, making the observed flatness a natural consequence rather than a fine-tuned coincidence. A third problem inflation solved was the origin of structure. The Big Bang model alone does not naturally produce the seeds from which galaxies and clusters and walls eventually grow. Inflation provides such seeds. During the inflationary expansion, quantum fluctuations in the inflaton field, the field that drives the expansion, are stretched to macroscopic scales. These fluctuations become the initial density variations from which all later structure develops. The pattern of density variations predicted by inflation matches, in detail, the pattern observed in the cosmic microwave background. This is one of inflation's most important successes. The predictions of inflation also include a specific prediction about the statistical properties of density variations. The variations should be approximately scale invariant, meaning that fluctuations of different sizes have similar amplitudes when expressed as fractions of the background density. The variations should also be approximately Gaussian, meaning that their statistical distribution follows the standard bell curve. These predictions have been tested with extraordinary precision against measurements of the cosmic microwave background. The data confirms the predictions to a high degree of accuracy. The connection to the Great Wall is that, given the initial conditions specified by inflation, the subsequent evolution of structure is largely determined by gravity acting on the density variations. The growth proceeds through well-understood physics, and the resulting structures should have specific statistical properties. The probability of finding very large structures is calculable from the inflationary initial conditions and the subsequent gravitational evolution. The calculations consistently produce the result that structures larger than approximately 1.2 billion light-years should be extremely rare. They should occur in the observable universe at frequencies that are very small, possibly less than once. The Great Wall, at 10 or 15 billion light-years, exceeds this expectation by a substantial margin. The structure could in principle still be consistent with inflation, but only if it represents an exceedingly rare statistical fluctuation. The question of how rare such a structure is, given the inflationary framework, has been the subject of multiple analyses with somewhat differing conclusions. Some analyses find the Great Wall consistent with inflation at the level of a 1 in 1,000 or 1 in 10,000 fluctuation. Others find the inconsistency much more severe. The discomfort with the Great Wall is not, therefore, a discomfort with inflation as such. Inflation is one of the most successful theories in modern cosmology, supported by many independent lines of evidence. The discomfort is more specific. It is the discomfort of finding, in the universe, something that the standard framework predicts should be improbable to a degree that is at least suggestive and possibly definitive. Whether the structure represents a true challenge to inflation, or merely a rare statistical event that inflation can accommodate, depends on details that are not yet settled. If the structure does eventually require revising the inflationary picture, the implications would be substantial. Inflation underlies most of modern cosmology. Modifying it in significant ways would have consequences for the predicted statistics of the cosmic microwave background, for the formation of structure at all scales, and for the dynamics of the very early universe. The Great Wall, in this respect, is not just an interesting curiosity. It may be one of the windows through which our current cosmological picture is eventually revised. There is a particular intellectual discipline required in any science that depends on rare events and statistical patterns. The discipline involves distinguishing between real anomalies, actual features of nature that the existing theory does not explain, and apparent anomalies that turn out, on closer inspection, to be artifacts of how the data was collected or analysed. The history of physics and astronomy contains many examples of both. Some apparent anomalies have led to genuine new discoveries. Others have dissolved into nothing when the relevant systematic effects were properly accounted for. The example most cited in physics is the supposed faster-than-light neutrinos detected by the Opera experiment in 2011. For several months, the result was the subject of intense discussion. If real, it would have required revising special relativity, with implications throughout physics. After careful investigation, the result was traced to a faulty cable connection. The neutrinos were not actually moving faster than light. The apparent anomaly was a measurement error, and once the error was identified, the result disappeared. The example most cited in astronomy is the so-called Hubble bubble, a proposed local underdensity in the universe that some researchers argued could explain certain discrepancies in measurements of cosmic expansion. The proposal was taken seriously for a time, but improved measurements eventually showed that the proposed bubble did not exist in the form required. The discrepancies in expansion measurements have other causes, which are still being investigated. The general lesson is that apparent anomalies in data are common, and most of them do not survive careful scrutiny. The base rate of false anomalies in any scientific field is substantial. This means that when a new anomaly is announced, the appropriate response is interest combined with skepticism. The interest is warranted because anomalies do occasionally lead to important discoveries. The skepticism is warranted because most anomalies turn out eventually to be artifacts. For the Great Wall, this calibration has been part of the scientific response from the beginning. The original 2014 announcement was greeted with appropriate interest and appropriate skepticism. Follow-up analyses were conducted to look for systematic effects in the gamma-ray burst data that might produce a false impression of clustering. Various possible explanations were considered, including selection effects in the burst catalogues, biases in the redshift measurements, and statistical fluctuations in the angular distribution of bursts. None of these explanations so far has succeeded in accounting for the observed clustering. The clustering persists across different datasets and different analysis methods. It is robust in a way that artifacts typically are not, but the possibility remains that some subtle systematic effect not yet identified is producing the apparent clustering. Gamma-ray bursts are detected by specific satellite instruments operating in specific modes. The efficiency of detection depends on the position of the burst in the sky, the brightness of the burst, and various other factors. The redshifts of the host galaxies are measured by ground-based telescopes, which themselves have their own selection effects. The overall sample of bursts with measured redshifts is not a random sample of all bursts that have occurred. It is a biased sample, and the biases are not perfectly understood. The careful position, then, is to acknowledge that the wall might be real and might be a real challenge to the cosmological principle, while simultaneously acknowledging that it might also be an artifact of the data collection process. The evidence so far favours the first possibility. The clustering is statistically significant by every method that has been applied to it. But the second possibility cannot be entirely ruled out. New data may eventually clarify the situation in either direction. This is the normal state of affairs in observational cosmology. Many apparent features of the data are tentatively classified as real while remaining subjects of continuing investigation. The Hubble tension, the various anomalies in the cosmic microwave background, the large-scale flows of galaxies, and various other features are all in similar status. They might all be real signs of new physics. They might all be artifacts. Most likely some are real and some are artifacts, and the difficulty is in determining which is which. For the listener trying to make sense of all this, the appropriate posture is patient interest. The science is in progress. The Great Wall is real until shown otherwise, but its implications remain provisional. The story may evolve over the coming decades as new data accumulates and new analyses are performed. The conclusions will be revised, perhaps modestly, perhaps dramatically. This is not a sign that the science is broken, it is a sign that the science is healthy. Real questions are being asked, real evidence is being gathered, and real reasoning is being applied to interpret the evidence. The wall is one of the questions. It may or may not turn out to be a feature of the universe in the long run. Either way, the process of investigating it has been, and continues to be, an example of how cosmology actually works. The Hercules Corona Borealis Great Wall is not the only large-scale structure that astronomers have identified. It is the largest by a substantial margin, but it is part of a population of very large structures that have been discovered over the past several decades, each of which has provoked its own discussion about the limits of the cosmological principle and the formation of structure in the universe. The first of these to be identified was the CFA2 Great Wall, discovered in 1989 by Margaret Geller and John Huchra of the Harvard-Smithsonian Center for Astrophysics. The CFA2 Wall is a sheet of galaxies approximately 500 million light-years long, located relatively close to Earth at distances of about 200 to 300 million light-years. At the time of its discovery, it was the largest known coherent structure in the universe, and its existence was significant because it suggested that the cosmic web extended to scales larger than had previously been mapped. The wall was identified through a careful survey of galaxy positions and redshifts, and it's played an important role in establishing the modern understanding of the cosmic web. In 2003, a much larger structure called the Sloan Great Wall was identified by researchers analysing data from the Sloan Digital Sky Survey. The Sloan Great Wall is approximately 1.4 billion light-years long, making it nearly 3 times the size of the CFA2 Wall. It was, at the time of its discovery, the largest known structure in the universe. The Sloan Wall is located at a distance of approximately 1 billion light-years from Earth, and it is composed of approximately 10,000 galaxies arranged in a complex of clusters and superclusters. The Sloan Great Wall is interesting in part because it is just at the edge of the cosmological correlation length, the theoretical maximum size for coherent structures. At 1.4 billion light-years, it is slightly larger than the theoretical limit of approximately 1.2 billion light-years, but only by a small amount. The discrepancy can be accommodated within the standard model as a statistical fluctuation. Since the predicted distribution of structure sizes does not have a sharp cutoff at the correlation length, but rather an exponential decline, the Sloan Wall is improbable, but not impossible. Several other very large structures have been identified in subsequent years. The Huge Large Quasar Group, identified in 2013, is a cluster of approximately 73 quasars arranged in a complex of structure approximately 4 billion light-years across. Quasars are the bright nuclei of distant galaxies, and the existence of such a large cluster of them suggests that the galaxies hosting them are arranged in a corresponding large-scale structure. The huge LQG is therefore a serious challenge to the cosmological principle, since it substantially exceeds the correlation length even by the standards of the Sloan Wall. The giant GRB ring, identified in 2015, is another structure traced by gamma-ray bursts. It consists of 9 bursts arranged in a roughly circular pattern with a diameter of approximately 5.6 billion light-years. The probability that 9 bursts would happen to fall on such a circular arrangement by chance is low, and the structure has been interpreted as evidence of an underlying ring-like distribution of matter at the same distance. The exact nature of the ring remains debated, but it is another example of a very large structure that the standard cosmological model has difficulty accommodating. The giant arc, identified in 2021, is a structure approximately 3.3 billion light-years across, traced by quasars and their associated absorption features. It was identified by a team of astronomers led by Alexia Lopez at the University of Central Lancashire. Like the other large structures, it appears to violate the cosmological principle's predictions, and its existence has added to the accumulating evidence that very large structures are more common than the standard model predicts. The Hercules Corona Borealis Great Wall, at 10 or 15 billion light-years, is substantially larger than any of these other structures. It is the most extreme example of a phenomenon that appears, with decreasing frequency, at progressively smaller scales. The CFA2 wall is large but accommodatable. The Sloan Wall is larger but still within the range of statistical fluctuation. The huge LQG and the giant arc are larger still and more difficult to explain. The Hercules Corona Borealis Great Wall pushes the issue to its sharpest expression. Taken together, these structures suggest that the cosmic web has more variation than the standard model predicts. There are too many large structures, and the largest ones are too large. The pattern is consistent across multiple independent observations, using different methods to trace the underlying matter distribution. The accumulating evidence is one of the reasons that cosmologists are increasingly willing to consider that the cosmological principle may need to be modified at very large scales. The Great Wall is therefore not an isolated anomaly. It is the most extreme example of a broader pattern, The pattern, taken as a whole, may eventually require a revision of the cosmological framework, or it may eventually be accommodated within a refined version of the existing framework. Either way, the picture that emerges will be richer than the smooth, uniform universe that the simplest version of the cosmological principle would suggest. It's worth taking a moment to look at the full hierarchy of cosmic structures, from the smallest scales to the largest, in order to place the Great Wall in context. The universe is organized at many different levels, and each level has its own characteristic scale, its own characteristic dynamics, and its own characteristic features. Understanding the hierarchy helps clarify what the Great Wall is and where it sits among the other things that exist. At the smallest scales relevant to astronomy, there are stars. A typical star is approximately the size of the Sun, about 1 million kilometers across, with a mass roughly that of the Sun. Stars are the basic units of nuclear activity in the universe. They produce the energy that lights up galaxies, the heavy elements that compose planets and life, and the explosions that produce gamma-ray bursts. There are approximately 10 to the 23rd power stars in the observable universe. Each is its own coherent object held together by its own gravity, fusing hydrogen and other elements at its core. Above the level of individual stars are stellar systems. Most stars exist in pairs or larger groups, with planets orbiting some of them. The Sun is somewhat unusual in being a solitary star, though its system of planets is comparable to many others. The scale of a typical stellar system is a few light hours to a few light days across, depending on how broadly the system is defined. Beyond the immediate planetary system, many stars have extended halos of small bodies, the Oort cloud in the case of the Sun, that extend out to perhaps a light year or more. Above stellar systems are galaxies. A typical galaxy contains anywhere from a few million to a few trillion stars, depending on its size. The Milky Way contains approximately 200 billion stars and is about 100,000 light-years across. Galaxies are gravitationally bound systems, with their stars orbiting around a common center under the influence of the galaxy's combined gravitational field. Most galaxies have a substantial component of dark matter, which provides most of the gravitational mass even though it does not emit light. Above individual galaxies are galaxy groups, small clusters of galaxies bound together by gravity. The local group, which contains the Milky Way and Andromeda, and several smaller galaxies, is a typical example. Galaxy groups contain perhaps a few dozen galaxies and are a few million light-years across. They are dynamically active, with their member galaxies in orbit around each other, and occasionally colliding or merging. Above galaxy groups are galaxy clusters, larger collections that can contain hundreds or thousands of galaxies bound together by gravity. The Virgo cluster, the nearest large galaxy cluster to the local group, contains approximately 1,500 galaxies and is about 15 million light-years across. Galaxy clusters are the largest gravitationally bound structures in the universe. Beyond the cluster scale, gravity is not strong enough to overcome the expansion of the universe, and structures are no longer truly bound. Above clusters are superclusters, which are large concentrations of galaxy clusters that are not fully bound but are nevertheless coherent structures within the cosmic web. The Virgo supercluster contains approximately 100 galaxy groups and clusters and is about 110 million light-years across. The Laniakea supercluster, identified in 2014, is much larger, approximately 500 million light-years across and containing about 100,000 galaxies. Laniakea is the local supercluster that includes the Virgo supercluster as one of its components. Our Milky Way is therefore within the local group, which is within the Virgo supercluster, which is within the Laniakea supercluster. Above superclusters are the largest structures of the cosmic web, the walls, the long filaments, the great voids. The Sloan Great Wall, at 1.4 billion light-years, is an example. The Hercules Corona Borealis Great Wall, at 10 to 15 billion light-years, is the most extreme example. These structures are not bound by the gravity in any meaningful sense. They are coherent patterns in the distribution of matter, organized by the gravitational and cosmological history of the universe, but their components are spreading apart with the expansion of space, rather than orbiting around any common center. Above the largest structures of the cosmic web is the observable universe as a whole, approximately 93 billion light-years in diameter. Beyond the observable universe, the universe presumably continues, but we cannot see it. The cosmic horizon, the boundary of the observable universe, is not a physical boundary, but a limit on our access. Light from beyond the horizon has not had time to reach us in the age of the universe. The Great Wall in this hierarchy sits at the upper end. It is the largest known organized structure within the observable universe. There may be larger structures we have not detected, but as of the time of this recording, the Great Wall is the largest entry in the catalogue. It occupies, in this sense, a position of distinction in the cosmic taxonomy. It is the largest thing we know about, and the fact that we know about it is itself an achievement of the methods we have developed to study a universe whose scales would otherwise overwhelm us. The cosmic web is composed of filaments, walls, and clusters of matter, but the majority of the volume of the universe is taken up by something else entirely, the voids. These are enormous regions of nearly empty space where the density of galaxies is dramatically lower than the cosmic average. The voids are the dark spaces between the bright filaments and walls. They are vast, common, and often surprisingly empty. A typical cosmic void is a roughly spherical region tens to hundreds of millions of light-years across, with a density of galaxies perhaps 10% or less of the cosmic average. Some voids are larger. The Bootes void, discovered in 1981, is approximately 330 million light-years across and contains only about 60 known galaxies. The giant void, identified in cosmic microwave background measurements, may be more than 1 billion light-years across, though its existence and properties remain debated. The voids are not perfectly empty. They contain some galaxies, some intergalactic gas, and presumably dark matter at lower density than in the filaments. But compared to the filaments, they are essentially empty. The contrast is striking. If you were able to travel through the universe at large scales, you would spend most of your time crossing voids, with occasional encounters with the bright filaments and walls of the cosmic web. The walls are the exceptions, the voids are the rule. The Hercules Corona Borealis Great Wall is itself surrounded by voids, and contains internal voids as well. The structure is not a solid mass of galaxies, but a complex network of filaments and sheets, with empty regions woven throughout. The total mass of the wall, taken as a single structure, is enormous, possibly equivalent to many thousands of typical galaxy clusters combined. But the matter is spread across a volume so vast that the average density within the wall, while higher than the cosmic average, is still very low in absolute terms. The wall is dense by comparison to the voids around it. By comparison to the interior of a star or a galaxy, it is essentially empty. The existence of voids is a natural consequence of the same process that produces walls and filaments. As matter collapses gravitationally into denser regions, the regions it leaves behind become emptier. Voids grow at the expense of the matter that flows out of them and into the surrounding structures. The size and number of voids in the cosmic web is a measurement that cosmologists use to test theories of structure formation. The voids should have specific statistical properties, particular distributions of sizes, particular relationships to the surrounding structures, that the theories predict and the observations can confirm or challenge. The largest voids are interesting in their own right, in a way that parallels the interest of the largest walls. Just as the Great Wall pushes against the theoretical limits on coherent structure sizes, the largest voids push against the theoretical limits on coherent empty regions. The cold spot in the cosmic microwave background, for example, has been suggested to be associated with a large void at moderate redshift, though the interpretation remains debated. If real, such a void would represent an extreme of the cosmic web at the opposite end from the Great Wall, an extreme of emptiness rather than concentration. What you would see if you were inside a cosmic void is something like what we currently see when we look out from the Milky Way. The night sky would contain stars within whatever galaxy you happen to be in, but the distance to the next galaxy would be substantially greater than the distance from the Milky Way to Andromeda. The cosmic web, viewed from inside a void, would be primarily visible as a distant background of light from the surrounding walls and filaments, with most of the foreground being almost completely empty. The voids are a reminder that the universe is mostly empty. Even within the cosmic web, where matter is concentrated, the density of matter is low. Outside the cosmic web, in the voids, the density is lower still. The total fraction of the universe occupied by stars, planets, gas clouds, and all the other forms of matter we know about is very small, much less than 1% of the total volume. The rest is space, with at most a faint scattering of particles per cubic meter, stretching for billions of light-years in every direction. There is something settling about this fact. The universe is enormous, and the structures it contains are extraordinary in their complexity and beauty. But the dominant feature of the universe is emptiness. The walls and filaments and galaxies are the exceptions. The voids are the background. Whatever is concentrated has to be concentrated against the background of what is not. The Great Wall, magnificent as it is a rare local concentration within a universe that is, taken as a whole, more empty than full. The bright pattern of the cosmic web is woven across a vastly larger fabric of darkness, and the darkness, in its quiet way, is where most of the universe lives. In April 2025, more than a decade after the original discovery, the same team that had identified the Hercules Corona Borealis Great Wall published a new analysis that substantially revised the understanding of the structure. The new analysis was led by Istvan Horvath, with John Hackler as co-author, and used an updated and expanded catalogue of gamma-ray bursts to re-examine the clustering pattern that had first revealed the wall's existence. The new dataset included 542 gamma-ray bursts with measured redshifts, drawn from observations primarily by NASA's Fermi Gamma Ray Space Telescope and the Neil Gehrels Swift Observatory through 2018. This was substantially more data than had been available for the original 2014 analysis, which had been based on a smaller burst catalogue. With the additional data, the statistical analysis could be more precise, and the boundaries of the wall could be mapped more accurately. The conclusions of the new analysis were striking. The wall, the team found, extends across a larger range of redshifts than previously calculated. The original analysis had identified the structure at redshifts of approximately 1.6 to 2.1. The new analysis extended the range to approximately 0.33 to 2.43. This represents a significant increase in the depth of the structure along the line of sight from Earth. Parts of the wall in this reviewed picture are substantially closer to Earth than had been recognized in the original analysis. Other parts are at similar distances to the original estimates. The overall structure is, by these measurements, larger than previously thought. The size of the wall in its longest dimension was previously estimated at approximately 10 billion light-years. The new analysis suggests that the actual extent may be closer to 15 billion light-years. This is roughly 1.5 times the previous estimate. It represents an extraordinary value, comparable to a substantial fraction of the diameter of the observable universe and well in excess of any other structure that has been identified. The implications of the larger size are significant. The discrepancy between the wall and the standard theoretical limits on coherent structure formation becomes substantially worse. If the original size of 10 billion light-years was already about 8 times the theoretical correlation length, the new size of 15 billion light-years is about 12 times the correlation length. The probability of such a structure forming through standard gravitational growth becomes correspondingly more remote. The wall in this updated picture is an even more severe challenge to the cosmological principle than had previously been recognized. The paper containing these results was submitted in early 2025 and posted to the RXIV preprint server. It is in the process of formal peer review at the time of this recording, but the results have already been widely discussed in the cosmology community. The team's conclusion is that the existence of such a structure may require modifications to the standard cosmological model, including possibly the introduction of new physical mechanisms or modifications to the inflationary picture of the early universe. There were also methodological refinements in the new analysis. The team used updated statistical techniques to evaluate the significance of the clustering, and they explicitly considered various possible sources of systematic error in the burst data. The analysis confirmed that the clustering was statistically significant by every test that was applied. The probability that the observed pattern could have arisen by chance, under a uniform underlying distribution, was very low, comparable to or smaller than the probabilities estimated in the original 2014 work. The team also noted that some nearby gamma-ray bursts, which had not previously been recognized as part of the wall, appear to be associated with the structure when the larger redshift range is considered. This suggests that the wall extends through regions of the universe that are accessible to other observational methods, including ground-based galaxy surveys. In principle, the wall could be cross-checked using independent measurements of galaxy density in the relevant directions and at the relevant distances. Such cross-checks have not yet been published, but they would be expected to follow as the data and analysis methods develop. The 2025 paper has, in this sense, opened a new phase in the study of the Great Wall. The structure is larger than was previously thought. It extends through a wider range of distances. It is closer to Earth in some parts than had been recognized. the theoretical problems with its existence are correspondingly sharper, and the opportunities for cross-checking the result through independent methods are correspondingly greater. The conversation that began with the 2014 discovery has not concluded. It has, if anything, intensified, with the new data confirming and extending the original result while raising new questions about how to interpret it. The wall remains the largest known structure in the universe. As of 2025, it is also substantially larger than it had previously been considered to be. The implications of this revision are still being worked out, and they will continue to be worked out in the years and decades ahead as further data is collected and further analyses are performed. 15 billion light-years is a difficult number to feel. It's difficult to feel 10 billion light-years, but 10 billion at least has the virtue of being a familiar order of magnitude in cosmology. The age of the universe is about 13.8 billion years, expressed as a number with the same set of digits. The age can be visualized, at least loosely, as a long stretch of cosmic history. 15 billion light-years is harder to visualize, because it exceeds the age of the universe expressed in light-years and approaches a substantial fraction of the diameter of the entire observable universe. The observable universe is approximately 93 billion light-years in diameter. The diameter exceeds the age of the universe in light-years because the universe has been expanding throughout its history, and the regions of space from which the most distant light has been arriving have themselves moved farther away during the light's transit. The light that reaches us today, from objects at the most distant accessible distances, was emitted from regions that have since moved much farther away than the light's travel distance might suggest. The result is a sphere of observability that, in present-day distances, is much larger than the distance light has actually travelled. 15 billion light-years is, then, approximately 1/6 of the diameter of the observable universe. To say that a single structure is 1/6 as large as everything we can possibly see is to make a claim that is, on its face, almost difficult to credit. The universe has not had time, by standard reasoning, to produce a structure of this size through normal gravitational dynamics. The very largest scales of the cosmic web, in standard simulations, are still much smaller than what the wall appears to be. Something unusual is going on. The question is what? One possibility is that the size estimate is wrong. The 15 billion light-year figure comes from the 2025 reanalysis, and it depends on specific assumptions about how to interpret the burst data. If those assumptions are slightly off, the true extent of the structure could be different, possibly smaller, possibly even larger. The error bars on the measurement are not negligible. The structure might be 10 billion light-years across, as in the original analysis. It might be 12 or 13 billion. The 15 billion figure is a specific value that emerges from a specific analysis, not a value that is independently confirmed by other methods. Another possibility is that the structure is real and its size is approximately what the recent analysis suggests, but that the standard cosmological model can accommodate it after all. Various extensions of the standard model, modifications to inflation, alternative theories of dark energy, exotic forms of dark matter, could in principle allow larger structures to form than the simplest version of the model predicts. The cost of these extensions is that they make the theory more complicated and introduce parameters that have to be determined from other observations. The benefit is that they could explain the wall without requiring the cosmological principle to be abandoned. A third possibility is that the cosmological principle itself is wrong or at least incomplete. The principle is an assumption about how the universe is organized at large scales, and it has been supported by many observations but never definitively proven. If the wall is real and as large as the recent analysis suggests, the principle may simply not apply at the largest scales. The universe may be more variable, more structured, more anisotropic than the principle assumes. This would be a major revision of cosmological theory, with consequences for many other parts of the field. A fourth possibility is that we are looking at something we do not yet understand. The wall might not be a single coherent structure in the usual sense, but something more exotic, perhaps a feature of the underlying geometry of space, perhaps a region influenced by physical processes that operated only at very early times, perhaps something else entirely. This standard categories, wall, filament, supercluster, might not fully capture what we are observing. New categories might be needed. These possibilities are not mutually exclusive. The actual situation might involve a combination of them. The size estimate might be partially overstated, but the structure might still be larger than the standard model can comfortably accommodate, requiring some modification of the model. The modification might involve some change to the cosmological principle, but not a complete abandonment of it. New observational and theoretical work might eventually reveal aspects of the structure that fit none of the existing categories. For now, the number stands, 15 billion light-years, a length that the universe is not supposed to have produced, a structure that the universe was not supposed to have made. The number sits in the data, awaiting interpretation. The interpretation will eventually come. In the meantime, the structure is there, and the question of how to understand it is one of the more interesting open problems in modern cosmology. Not every astronomer accepts that the Hercules Corona Borealis Great Wall is a real physical structure. There is a substantial minority of researchers who argue that the apparent clustering of gamma-ray bursts in the relevant region of the sky may be an artifact of how the data has been collected and analysed, rather than a reflection of an underlying overdensity of matter. The skeptical position is not unreasonable, and it deserves a careful presentation. The most common skeptical arguments focus on the limitations of the gamma-ray burst catalogue. The catalogue of bursts with measured redshifts is small, fewer than 1,000 bursts in total, out of the many thousands that have been detected without redshift measurements. The redshifts depend on follow-up observations of the host galaxies, which are not always possible. Bursts that occur in regions of the sky with poor visibility from major telescopes, or that occur during periods of bad weather, or whose host galaxies are too faint to be identified, may not have measured redshifts. The result is a biased sample. The bursts with redshifts are not a random selection from all bursts, they are the ones for which the follow-up observations happen to succeed. This selection bias could, in principle, produce apparent clustering patterns that do not reflect the underlying distribution of all Boreal bursts, if, for some reason, the follow-up observations are more successful in certain regions of the sky than others. The resulting catalogue of bursts with redshifts will be denser in those regions, regardless of how the underlying bursts are actually distributed. The clustering apparent in the Hercules Corona Borealis direction might be, under this interpretation, the result of more efficient follow-up in that region, rather than a real concentration of bursts. The proponents of the Great Wall have addressed this possibility in their published analyses. They have argued that the patterns of follow-up success do not, in fact, match the patterns of apparent clustering. The clustering is in directions where the follow-up should be neither more nor less successful than average. The selection effects that one might invoke to explain the clustering do not actually have the right properties. The clustering persists across various subsamples of the data, defined by different criteria, in ways that selection effects would not produce. A more sophisticated skeptical argument involves the statistics of structure size in cosmological simulations. The standard simulations produce a probability distribution of structure sizes that has a long tail. That is, very large structures are predicted to occur, just at low probability. The question is, how low? If the predicted probability of finding a structure as large as the Great Wall is 1 in 1,000, then finding one in the observable universe is improbable but not impossible. If the predicted probability is 1 in a billion, then the existence of the wall would essentially rule out the standard model. Different analyses have arrived at different values for the predicted probability. The variation comes from differences in how the simulations are set up, what statistical tests are applied, and how the comparison to the data is performed. Some analyses find the wall consistent with the standard model at the level of 1 in 1,000 fluctuation. Others find the inconsistency much more severe, a 1 in a million or even 1 in a billion fluctuation. Without consensus on the predicted probability, the implications of the wall for the standard model cannot be definitively determined. The skeptical position therefore has multiple strands. The structure might be an artifact of selection effects in the burst catalogue. The structure might be real but consistent with the standard model as a rare statistical fluctuation. The structure might be real but produced by some specific physical process that the simulations are missing. Each of these positions is held by some researchers, and the debate among them is ongoing. What makes the skepticism difficult to fully sustain is that the clustering has survived every specific test that has been proposed for it. When researchers have looked for the particular selection effects that might produce the clustering, they have not found them. When they have applied alternative statistical methods, the clustering has remained. When they have used independent datasets, the clustering has appeared in those as well. The robustness of the result across multiple methods and datasets is what has gradually moved the mainstream view toward accepting the wall as a real structure, even as theoretical questions about its origin remain unresolved. The skeptics nevertheless serve a useful function. They keep the analysis honest. They force the proponents to defend their conclusions against specific alternatives, and they identify possibilities that need to be considered. The eventual resolution of the question will require either definitively ruling out the skeptical alternatives or, if those alternatives turn out to be correct after all, revising the picture of the wall accordingly. Science proceeds through this kind of dialectic. The Great Wall is, at the moment, the consensus view, with a substantial minority of skeptics whose arguments are taken seriously but have not, so far, succeeded in dislodging the consensus. The conversation continues, the data continues to accumulate, the answers, eventually, will become clearer. To understand the skeptical arguments more fully, it helps to look at exactly how the gamma-ray burst catalogue is built and what its limitations are. The catalogue is, in a sense, a sample of the underlying population of all gamma-ray bursts that have occurred. But it is a sample drawn from a complex process, with many filters and selection effects between the original bursts and the entries in the catalogue. Each filter has the potential to introduce bias, and the cumulative effect of all the filters has to be carefully understood before strong conclusions can be drawn from the catalogue. The first filter is detection. A gamma-ray burst can only enter the catalogue if it is detected by some instrument. The instruments that detect bursts are the Swift Burst Alert Telescope, the Fermi Gamma-Ray Burst Monitor, and various other gamma-ray detectors in orbit around Earth. These instruments have the specific sensitivity thresholds and specific fields of view at any given moment. A burst that occurs in a region of the sky that is not being observed at the moment of the burst, or that is too faint to exceed the detection threshold, will not be detected. The catalogue therefore systematically misses bursts that are too faint to detect or that occur at unfortunate times relative to the instrument's pointing. The second filter is localization. Once a burst is detected, its position in the sky has to be determined precisely enough for follow-up observations to be possible. Different instruments provide different localization precisions. The most precise localizations come from instruments that can identify the X-ray or optical afterglow of the burst, which fades over hours to days following the gamma-ray emission itself. Bursts whose afterglows are too faint to detect, or which occur in regions where afterglow follow-up is difficult, may not be localized precisely enough for further study. The third filter is host galaxy identification. To measure the redshift of a burst, astronomers need to identify the galaxy in which the burst occurred and obtain a spectrum of that galaxy. The galaxy is typically identified by comparing the precise position of the burst to images of the relevant region of the sky. If the host galaxy is too faint to detect, or if the burst position is in a crowded region with multiple possible host galaxies, the identification may not be possible. Bursts without identified host galaxies cannot have measured redshifts and do not enter the catalogue of bursts with redshift information. The fourth filter is redshift measurement. Even when a host galaxy is identified, measuring its redshift requires spectroscopic observations with telescopes capable of obtaining the relevant spectra. The brightness of the host galaxy matters. Fainter galaxies require larger telescopes and longer exposure times. The position of the galaxy in the sky matters. Galaxies that are observable only from one hemisphere, or only at certain times of year, have less access to the available telescope time. The cumulative effect is that the bursts with measured redshifts are systematically biased toward those with brighter host galaxies, those in more accessible regions of the sky, and those that happen to occur when the relevant telescopes were available. Each of these filters introduces selection effects that can, in principle, bias the resulting catalogue. The question for any specific claim about the catalogue is whether the selection effects are strong enough to produce that claim. For the Hercules Corona Borealis Great Wall, the relevant claim is the clustering of bursts in a particular region of the sky at a particular redshifts. To dismiss the claim, one would need to identify a selection effect that produces excess bursts specifically in that region and at those redshifts. The proponents of the wall have argued that no such selection effect is plausibly large enough to account for the observed clustering. The skeptics have not been able to identify one in the data so far. There is, however, a deeper question that the selection effects raise. Even if no specific bias can be identified, the cumulative effect of many small biases might still be relevant. The catalogue of bursts with measured redshifts is not a random sample of the underlying burst population. It is a heavily filtered sample, with the filters themselves not fully understood. The conclusions drawn from this sample have to be taken with appropriate caution. This caution is exercised in the published analyses of the wall. The papers include extensive discussions of selection effects and of the limitations of the data. The clustering is reported as statistically significant under various tests, but the reports are honest about the uncertainties involved. The wall is a structure that the available data supports, with the available analyses, with the caveats that the data and analyses themselves entail. What this means, practically, is that the conclusion remains provisional. The wall is real to the best of our knowledge, but our knowledge is imperfect. Future data may strengthen the conclusion, or it may revise it. The history of similar claims in cosmology includes both the and outcomes, patterns that were eventually confirmed and patterns that eventually faded. Which outcome the wall will eventually follow is not yet known. The detection of the gamma-ray bursts that revealed the Great Wall came primarily from 2 satellite missions, both still in operation. The Neil Gehrels Swift Observatory, launched by NASA in November 2004, and the Fermi Gamma-Ray Space Telescope, launched in June 2008. Together, these 2 satellites have been the workhorses of gamma-ray burst observation for nearly 2 decades, and the catalogue of bursts they have detected is the foundation on which most modern understanding of these events depends. Swift was designed with a specific purpose: to respond rapidly to gamma-ray bursts and to study their afterglow emission at X-ray and ultraviolet wavelengths. The satellite carries 3 main instruments. The Burst Alert Telescope is a wide-field gamma-ray detector that watches a substantial fraction of the sky at any given moment, looking for the brief, intense gamma-ray signal of a new burst. When a burst is detected, Swift automatically slews, that is, rotates, to point its other 2 instruments at the burst location within seconds. The X-ray telescope and the ultraviolet/optical telescope then study the afterglow emission, which can persist for hours or days following the initial burst. The rapid response of Swift has been crucial for catching bursts in time to measure their precise positions and to identify their host galaxies. Fermi was designed with a broader purpose: to study gamma-ray emission from a wide range of cosmic sources, of which gamma-ray bursts are just one category. The satellite's main instrument is the Large Area Telescope, which observes high-energy gamma rays from across the sky. A secondary instrument, the Gamma Ray Burst Monitor, is specifically dedicated to detecting bursts and is sensitive to lower-energy gamma rays. The combination provides extensive coverage of the gamma-ray sky. Fermi cannot slew as quickly as Swift, so its burst localizations are typically less precise, but it detects bursts at a higher rate due to its larger field of view. Between them, Swift and Fermi have detected several thousand gamma-ray bursts over the years. Of these, a substantial fraction have been localized precisely enough for follow-up observations, and of those, several hundred have had their host galaxies identified and their redshifts measured. The accumulating catalogue of bursts with measured redshifts has been the primary tool for studying the large-scale distribution of bursts across the universe, including the discovery of the Great Wall. What the satellites actually see when they detect a burst is a brief surge of gamma-ray photons arriving at the detector. The burst lasts from a fraction of a second to several minutes. During that time, the gamma-ray flux from the source can exceed the flux from the rest of the sky, combined by an enormous factor. The instruments record the time, the energy, and the direction of arrival of each photon. The processing software identifies the burst, calculates its position, and sends an alert to follow-up observatories around the world. The whole sequence, from initial detection to public alert, takes seconds or minutes. The follow-up observations then begin. Ground-based telescopes, alerted to the burst position, point at the relevant region of the sky and look for the afterglow. The afterglow, which fades over time, is the optical or X-ray signal from the same source that produced the gamma-ray burst. By identifying the afterglow position precisely, astronomers can identify the host galaxy with high accuracy. Subsequent spectroscopic observations of the host galaxy provide the redshift, which combined with the position gives the 3-dimensional location of the burst in the universe. The data from each burst is recorded in the catalogue, with details including the burst position, the burst duration, the burst spectrum, the host galaxy properties, and the redshift. The catalogues maintained by Swift and Fermi, along with various other databases compiled by individual researchers, contain hundreds of entries with measured redshifts. The Great Wall was identified by analysing the statistical properties of these entries, looking for departures from the expected distribution. It is worth appreciating the technological achievement that all of this represents. The satellites are complex instruments, operating in the harsh environment of space, conducting precise measurements of extremely brief and rare events. The ground-based follow-up depends on a global network of telescopes with rapid communication and coordination. The data analysis requires sophisticated statistical techniques and substantial computational resources. The whole apparatus is the product of decades of development involving thousands of scientists and engineers, supported by major investments from multiple national space agencies. The Great Wall is, in this sense, a discovery enabled by the entire infrastructure of modern high-energy astronomy. The structure is real, but our ability to see it depends on a sequence of technological capabilities that have only relatively recently come together. Earlier generations of astronomers, with their less capable instruments, could not have detected such a structure even if they had been looking. The wall has always been there. We have only recently developed the means to know about it. The Great Wall has been subjected to extensive statistical analysis since its initial discovery. Multiple research groups using multiple methods have examined the burst catalogue to test the significance of the observed clustering. The fact that the clustering survives these tests is one of the main reasons the structure is taken seriously as a real feature of the universe rather than a statistical artifact. The simplest test asks whether the bursts in a particular region of the sky and at a particular range of redshifts are more numerous than would be expected by chance, given the total number of bursts in the catalogue and the assumed uniform underlying distribution. The calculation involves binning the bursts by sky position and redshift, counting the number in each bin, and comparing the counts to what a uniform distribution would predict. If the counts in some bins are substantially higher than the prediction, the clustering is statistically significant. For the wall, this kind of test consistently produces highly significant results. The number of bursts in the Hercules Corona Borealis region at the relevant redshifts is substantially larger than the expected number under uniformity. The exact significance depends on the specific binning and the specific statistical test used. But the values are routinely better than 1 in 100. That is, the probability that the observed clustering could have arisen by chance is less than 1%. A more sophisticated test asks whether the clustering pattern has the angular size that would be expected for a real large-scale structure. Real structures should produce clustering that is coherent across the relevant angular scales. That is, the excess bursts should be distributed in a connected pattern, not in a random scattering of small clumps. Statistical methods that test for spatial coherence consistently find that the wall pattern is coherent at the relevant scales. This is more consistent with a real structure than with a random accumulation of unrelated bursts. Another approach is to use a different statistic entirely. The angular two-point correlation function measures how the density of bursts varies with separation across the sky. If bursts are randomly distributed, the correlation function should be flat at all separations. If they are clustered, the correlation function should rise at small separations and fall to 0 at large separations. For the wall region, the correlation function shows an excess at separations corresponding to the angular size of the wall, again consistent with a real coherent structure. Multiple research groups have applied these and other statistical tests to the data, sometimes with slightly different conclusions about the exact significance of the result. The general finding, however, is that the clustering is statistically significant by most reasonable tests, and that the significance has increased rather than decreased as the burst catalogue has grown over time. If the clustering were an artifact of small sample size or selection effects, one would expect the significance to decrease or remain constant as more data accumulated. Instead, it has increased. This is the behavior of a real signal, not of noise. There have also been tests designed specifically to look for systematic effects that might produce a false impression of clustering. Various researchers have examined the spatial distribution of telescope coverage, the efficiency of follow-up observations as a function of sky position, the dependence of redshift measurements on host galaxy brightness, and various other potential sources of bias. None of these examinations has identified a systematic effect large enough to account for the observed clustering. The patterns in the data look like the patterns one would expect from a real underlying structure, not the patterns one would expect from observational biases. This does not definitively rule out the possibility of some subtle, systematic effect that has not yet been identified. The data is complex and the analyses are necessarily incomplete, but the existing tests have been thorough enough that the burden of proof has shifted. The default assumption, at this point, is that the wall is real until convincing evidence to the contrary is presented. The default for many years was the opposite. that the structure was probably an artifact until proven otherwise. The shift in default reflects the accumulating weight of evidence. What the statistical tests cannot tell us is what the wall actually is, beyond the fact that it is a real overdensity in the burst distribution. The tests confirm the existence of clustering, but do not address the question of how that clustering came to be. For that, theoretical work is required, and the theoretical work, as we have seen, has not yet produced a definitive answer. The wall, in this sense, is on solid empirical ground, but uncertain theoretical ground. The data supports its existence. The theory has difficulty accommodating it. The combination is what makes it interesting, and what continues to drive research on the structure. The statistical tests have done their work. They have established that the structure is there. The work that remains is to understand why. The discussion of distance has been implicit throughout this story, but it is worth pausing to think more carefully about what distance means at the scales we have been discussing. The relationship between time and space at cosmic scales is not the same as the relationship at the human scale, and the differences matter for understanding what we are actually looking at when we study the Great Wall. At the human scale, time and space are essentially separate. You exist at a specific time, in a specific place, and you can move through space without significantly affecting time, and time passes for you without significantly affecting your spatial position. The two coordinates are independent. They can be measured separately. They have independent meaning. At cosmic scales, this separation breaks down. The universe is expanding, and the expansion means that the distance between any two objects is changing over time. The rate of change depends on the distance. More distant objects are receding faster than nearer ones. This relationship is described by the Hubble constant, named after Edwin Hubble, which gives the rate of expansion in units of velocity per unit distance. The current value of the Hubble constant is approximately 70 km per second per megaparsec, which means that an object 1 megaparsec away is moving away from us at 70 km per second, and an object 10 megaparsecs away is moving away at 700 km per second. The implications of the expansion for the meaning of distance are substantial. There are several different definitions of distance that astronomers use at cosmic scales, each appropriate for different purposes. The comoving distance is the distance between two objects in the present-day expanded universe. The proper distance is the distance at any specific moment, accounting for the expansion. The light travel distance is the distance light has actually travelled from the source to the observer. The angular diameter distance is the distance that gives the correct angular size for an object of known physical size. These different distances can give different numerical values for the same pair of objects, and the differences become significant at large redshifts. For the Great Wall, the various distances are not all the same. The light from the wall has travelled approximately 10 billion years to reach us. The comoving distance to the centre of the wall is somewhat greater than 10 billion light-years, because the universe has expanded during the light's transit. The current proper distance, in present-day terms, is greater still. The wall's actual extent in present-day distances is somewhat larger than the extent we observe, because what we see is the wall as it was when the light left, and the structure has expanded along with the universe since then. These distinctions can be confusing, but they have practical consequences. When we say that the wall is 10 billion light-years across, what we mean depends on which definition of distance we are using. The light travel distance from one end to the other, measured during the universe at the time the light left the wall, was approximately 10 billion light-years. The present-day proper distance, if we could somehow measure it instantaneously, would be somewhat larger, perhaps 15 or 20 billion light-years. The structure is even larger in the present than it was in the past, because everything in the universe has been expanding. There is also a deeper conceptual point. When we look at the wall, we are not looking at a single moment in the structure's history. We are looking at a range of moments, because the light from different parts of the wall has travelled different distances and was emitted at different times. The light from the nearer parts of the wall left more recently than the light from the more distant parts. The image we construct, if we could construct one, would not be a snapshot of a single moment, but a composite of many moments, each from a slightly different time in the wall's history. This is true of everything in astronomy, but the timescales involved with the wall make the point particularly vivid. The depth of the wall along the line of sight is about 1 billion light-years. The light from the near edge of the wall left about 1 billion years more recently than the light from the far edge. When we observe the wall, we are observing a structure that, in its own internal time, spans 1 billion years between its near and far parts. This is itself an enormous span of cosmic history. The structure exists. The structure has existed for billions of years. The structure continues to exist, but what we see when we observe it is not the structure as it is now. It is the structure as it was, in a range of moments stretching across a billion years of its own history. The current state of the wall is something we cannot directly observe. We can only see the past, and the past is what we are looking at when we look at the wall. The light arriving at our telescopes from the Great Wall is approximately 10 billion years old. It left its sources when the universe was approximately 3 to 4 billion years old, less than a third of its current age. The conditions in the universe at that time were substantially different from the conditions today, and the galaxies we are seeing through this light are galaxies in an earlier stage of cosmic evolution than the galaxies we are familiar with from our own local environment. Early galaxies were, on average, smaller than modern galaxies. They had not yet undergone the many mergers and accretions that have built up the larger galaxies of the present-day universe. They were, on average, more actively forming stars. The rate of star formation in the universe was higher in the past than it is today, with a peak occurring at redshifts of approximately 1.5 to 2.5, exactly the range in which the Great Wall is located. The galaxies of the Wall, as we see them, are in the most active period of star formation that the universe has ever experienced. The chemical composition of these early galaxies was also different from that of modern galaxies. The heavy elements, anything heavier than helium, are produced primarily in stars, and they accumulate in the universe over time. At the time the light from the wall was emitted, fewer generations of stars had passed than at present, and the abundance of heavy elements in the gas from which new stars were forming was substantially lower than it is today. The galaxies of the wall would have been, on average, more metal-poor than modern galaxies. The morphology of early galaxies was also different. Spiral galaxies of the kind we see locally were less common at high redshifts. More common were irregular galaxies, peculiar galaxies, and various transitional forms that have largely disappeared from the modern universe through evolution and merger. The galaxies of the wall, as we see them, would have appeared lumpy and irregular in ways that the well-organized spiral arms of the Milky Way are not. What we cannot directly observe is what the wall looks like now. The light from the present-day wall, if any could reach us, would have to travel 10 billion years to arrive, and over that time the universe would have continued to expand, the distance to the wall would have increased, and the conditions everywhere would have changed. We will not, in any practical sense, ever see the present-day wall. We will only see successively older versions of it, as we continue to receive light that left it at successively earlier moments. This is a strange relationship to have with a physical object. The wall exists. The wall has presumably continued to evolve since the light we observe left it. Galaxies within the wall have merged, new stars have formed, old stars have died, the chemical composition has changed. The wall as it is now is, in some ways, different from the wall as we see it, but we have no access to the wall as it is now. We have access only to its past, and the past we have access to is itself, a slowly changing past, with the light arriving today carrying information from 10 billion years ago, the light arriving in 1,000 years carrying information from a slightly more recent moment, and so on. The wall is not, in this sense, a fixed object that we are gradually learning about. It is a continuously changing object, whose changes we will see only with a delay of 10 billion years. By the time we see the changes that are happening in the wall today, neither we nor our species, nor probably any of the institutions that have studied the wall will exist. The light from today, if it is detected by anyone, will be detected by some far future intelligence, possibly elsewhere in the universe, possibly nowhere at all. There is something poignant in this. The wall sends us news from a very long time ago. The news takes 10 billion years to arrive. By the time it arrives, the events it reports have long since passed, and the structures it describes have long since evolved into something else. We are looking at history in the same way that all astronomy is looking at history, but on a scale that exceeds even the age of the Earth by more than a factor of 2. This is not a problem for the science. The history is exactly what we want to study, because it tells us about how the universe was at an earlier moment in its evolution. The fact that we cannot see the present is not, for astronomical purposes, a limitation. It is simply the nature of the work. The light arrives when it arrives, carrying what it carries, and we extract from it what we can. The Great Wall is, in this respect, a kind of cosmic letter, sent long ago, read carefully today with the author and the events long gone, but the message arriving nevertheless. It is worth pausing on a specific fact about the Great Wall. The light we observe from it began its journey before the Earth existed. The Earth, along with the Sun and the rest of the solar system, formed approximately 4.6 billion years ago. The light from the wall that we observe today left its sources approximately 10 billion years ago. The gap between these two numbers is about 5.4 billion years. For 5.4 billion years, the light travelled through space without a destination, without the Earth, without the Sun, without the planet that would eventually exist to receive it. This is, in some sense, a remarkable fact. The light was emitted into a universe in which the receiver did not yet exist. The receiver, Earth, the Sun, the entire history that produced the species and the technology and the institutions and the satellites and the people who now study the wall, had not yet come into being. There was no possibility, at the moment of emission, that the light would ever be detected by anyone, because no one existed to do the detecting. The light travelled through space anyway, because that is what light does. The arrival of the light at Earth, 10 billion years later, depended on the formation of Earth itself in the intervening time. There is no plan in this. The light was not aimed at Earth. It was emitted in all directions from the galaxies of the wall, as light always is, and most of it has continued travelling in directions that will never intersect with any observer. The tiny fraction that happened to reach the eventual location of the Earth, and to arrive at a moment when the Earth happened to have the technology to detect it, is what we are working with. The accident is enormous. It is the kind of accident that requires the formation of a planet, the evolution of life on that planet, the development of intelligence in that life, the construction of telescopes and satellites by that intelligence, and the survival of the entire enterprise long enough for the light to arrive. Any of these steps could have failed. None of them did. This is a useful way to think about astronomy more generally. We are, in some sense, eavesdroppers on a universe that is not addressing us. The light that arrives at our telescopes was not sent to us. It was sent into space with no particular destination in mind, and we happen to be in its path. We extract information from it not because the information was meant for us, but because the information is encoded in the physical properties of the light. The wavelength, the intensity, the polarization, the timing. The information is there to be read by anyone who develops the tools to read it. We have developed those tools. We read what arrives. The light from the Great Wall is among the most ancient signals we routinely detect. Older light exists, the cosmic microwave background, emitted approximately 380,000 years after the Big Bang, is the oldest light that exists in the universe. But the gamma ray bursts from the wall are nearly as old, in the sense that they were emitted in the early universe and have been travelling toward us for the great majority of the universe's history. When we detect a burst from the wall, we are receiving a signal from a time before nearly all of present-day astronomy was possible, before life on Earth, before the chemical elements heavier than iron had been substantially distributed throughout the universe, before most of the stars now visible into the night sky existed. It is also worth thinking, briefly, about what this means for our understanding of our own situation. We exist on a small planet orbiting a small star in a small corner of a galaxy that is itself an unremarkable spiral galaxy in a typical region of the cosmic web. The light we receive from very distant sources tells us about regions of the universe that we will never visit, and that have no particular connection to us. The information is, in a strict sense, useless. It does not help us survive. It does not improve our material circumstances. We collect it because we want to know. The wall sent its light into a universe where the Earth did not yet exist. The Earth eventually formed, and on the Earth eventually emerged the kind of curiosity that builds satellites to detect that light. The two arrived at the same place at the same time, by a coincidence so vast that the word coincidence barely covers it. And the wall, knowing nothing of any of this, continues to send its light, to be received by whoever is there when it arrives. It is natural to wonder where we are in relation to the Great Wall. The structure is one of the most prominent features of the universe at its largest scales, and our own galaxy has to be located somewhere in the cosmic web. The question of where exactly deserves a careful answer, because the answer reveals something both about our position and about the structure of the universe more generally. The Milky Way is located in the Local Group, a small collection of about 30 galaxies bound together by gravity. The Local Group, in turn, is part of the Virgo supercluster, a much larger collection of about 100 galaxy groups and clusters spread across a region of approximately 110 million light-years. The Virgo supercluster is part of the Laniakea supercluster, an even larger structure approximately 500 million light-years across containing approximately 100,000 galaxies. Laniakea was identified as a coherent structure in 2014, the same year, by coincidence, that the Hercules Corona Borealis Great Wall was discovered. Laniakea is itself a relatively modest feature of the cosmic web. There are other superclusters of comparable or greater size scattered throughout the observable universe. Laniakea is not unusual in any particular respect. It is simply the local supercluster, the one we happen to be in. Its identification as a single coherent structure was based on detailed measurements of how galaxies in the relevant region are moving, with the boundaries of Laniakea defined by the locations where the gravitational influence of the structure gives way to the influence of neighbouring superclusters. The Hercules Corona Borealis Great Wall is not part of Laniakea. The two structures are entirely separate, located in different regions of the universe. Laniakea is, by cosmic standards, relatively nearby. Its centre is about 250 million light-years from the Milky Way. The Great Wall is approximately 10 billion light-years away. The two structures are separated by a vast volume of space containing many other structures of various sizes, with voids and filaments arranged in the patterns of the cosmic web. In terms of present-day distances, the Milky Way is not within the Great Wall. We are not part of the structure that the wall describes. The wall is, instead, a different region of the cosmic web, located in a direction away from us, at a distance that places it far beyond the range of any structure we are part of. When we observe the wall, we are looking outward from our own local environment into a region we have no direct connection to. There is, however, a more subtle sense in which we are connected to the wall. The wall is part of the cosmic web, and the cosmic web is a single connected structure that pervades the entire observable universe. The filaments around the Milky Way connect to other filaments that eventually connect in some indirect way to the filaments that compose the wall. The connection is loose, but in principle the network is continuous. The Milky Way is in one part of the network. The wall is in another part. The network connects them distantly. This connection is not meaningful in any direct physical sense. The Milky Way and the wall are too far apart to influence each other gravitationally to any detectable degree. The expansion of the universe is carrying them apart faster than any signal could be exchanged. They are, for all practical purposes, separate, but they are both parts of the same cosmic structure, the same network, the same overall pattern of matter distribution. There is also a meaningful sense in which the wall is part of our cosmic environment. Light from the wall reaches us. The wall is a feature of the universe we observe. It influences our maps of the cosmic web, our understanding of large-scale structure, and our theories of how the universe formed. The wall is not in our local supercluster, but it is in our observable universe. And the existence of the wall is part of the context in which we think about our own position. Some popular descriptions of the wall have suggested that it is, in some sense, threatening to us, that it might eventually engulf us, or that it has implications for our survival. These suggestions are not correct. The wall is enormously far away. It is moving away from us with the expansion of the universe faster than any signal could travel. It poses no physical threat. It will not engulf us. It is simply a feature of the universe that we have learned to detect. What it does is provide context. We exist in a universe whose largest known structure is 10 or 15 billion light-years across, located in a particular direction at a particular distance with particular properties. The structure does not affect us directly. But knowing that it exists changes how we think about the universe in which we live. It is the kind of knowledge that does not change our practical situation, but does change our understanding of where we are. And the change in understanding is, in itself, valuable. The Milky Way's specific location in the cosmic web is something that has been studied in detail in recent years, primarily through surveys of galaxy positions and motions in our local region of the universe. The picture that has emerged is one of substantial complexity, with our galaxy embedded in a network of structures of various sizes, all of them interconnected, and all of them moving in characteristic patterns. At the most local scale, the Milky Way is part of the local group, with Andromeda as its largest neighbour. The Milky Way and Andromeda are approaching each other at approximately 110 kilometers per second, and they are expected to collide in about 4 billion years. The collision will be slow and gradual by everyday standards, with the two galaxies merging over a period of approximately 2 billion years. The merger will produce a single large galaxy, sometimes called Milky, that will contain stars from both progenitors arranged in a new configuration. This merger is one of the dynamical events in the long-term future of the Milky Way that can be predicted with reasonable confidence. At the next scale up, the local group is part of the Virgo supercluster, which contains the Virgo cluster at its center, along with various smaller groups, including our own local group. The motion of the local group is influenced by the gravitational attraction of the Virgo cluster, which is pulling us toward it at approximately 270 kilometers per second. This motion is one component of what is called the peculiar velocity of the local group, its motion relative to the average motion of galaxies in our cosmic neighborhood. Beyond the Virgo supercluster, the situation becomes more complex. The local group's motion is also influenced by a region of high mass density called the Great Attractor, located approximately 250 million light-years away in the direction of the constellation Centaurus. The Great Attractor was identified in the 1980s through measurements of galaxy motions in our cosmic neighborhood. Galaxies in various directions all appeared to be moving toward a common point, and the point was named for the attraction that was apparently drawing them. The exact nature of the Great Attractor has been debated for decades, with the consensus view being that it is a large concentration of mass in the Laniakea supercluster, possibly associated with the Norma cluster or with a region called the Shapley supercluster. The Shapley supercluster, located beyond the Great Attractor at approximately 650 million light-years from Earth, is an even larger concentration of mass. Some analyses suggest that the Shapley supercluster, rather than the Great Attractor itself, is the primary source of the gravitational pull on our local cosmic neighborhood. The motion of the local group in this picture is the cumulative result of attraction from multiple nearby structures. What this means, in summary, is that the Milky Way is in motion through the cosmic web. We are moving relative to the cosmic microwave background at approximately 600 kilometers per second. Our motion has multiple components reflecting the gravitational influences of various structures around us. We are being pulled simultaneously toward Virgo, toward the Great Attractor, toward Shapley, and toward various other concentrations of mass. The net motion is a kind of weighted average of all these influences. We are not, however, moving toward the Hercules Corona Borealis Great Wall. The wall is too far away to have any measurable gravitational influence on the local group. The wall is also moving away from us, with the expansion of the universe faster than any motion we could undertake. The wall is a feature of the universe we observe, but it is not a feature that affects our trajectory. The position of the Milky Way in the cosmic web is therefore in some sense ordinary. We are in a typical region of the universe with typical motions and typical surroundings. The fact that we happen to be here, on this particular planet, around this particular star in this particular galaxy, is not because of any special property of our location. It is simply where we are. There is something meddling in this ordinariness. The Milky Way is not at the center of the universe. The Milky Way is not the largest or most important galaxy. The structures we are part of are not the largest or most important structures. We are in a normal location, doing normal things. Observing the universe from a position that is, by cosmic standards, completely undistinguished. What is distinguished is not our location, but what we are doing from that location. We are observing the universe, we are building maps of the cosmic web, we are discovering structures like the Great Wall that we could not have known about without our specific technological achievements. The doing is what makes us unusual. The Milky Way will continue to move through the cosmic web. It will eventually merge with Andromeda. It will eventually become a different galaxy than it currently is. The Great Wall will continue to exist, at 10 or 15 billion light-years away, sending us its ancient light. The relationship between these two facts is simply that they share a universe. Beyond that, there is no relationship at all. The existence of the Great Wall has implications for our understanding of the early universe. Whatever produced the structure happened in the relatively brief period between the Big Bang and the time the light from the wall was emitted, a period of approximately 3 to 4 billion years. The structure was already in place as we observe it by that point in cosmic history. Whatever produced it had to be a process that could operate on the timescales of the early universe and that could produce coherent structures on scales of 10 or more billion light-years. Standard cosmology offers a sequence of events for how the early universe evolved. After the Big Bang, the universe was an extremely hot dense plasma of subatomic particles. As it expanded and cooled, the particles combined into atoms, initially hydrogen and helium, with smaller amounts of lithium and beryllium. The first atoms formed approximately 380,000 years after the Big Bang, at which point the universe became transparent to light and the cosmic microwave background was released. From that point onward, the universe was filled with neutral atoms, mostly hydrogen, slowly cooling as the expansion continued. The first stars formed several 100 million years after the Big Bang, in the densest regions of the matter distribution. These first stars were massive, short-lived, and produced heavy elements in their cores that they then released through supernova explosions at the ends of their lives. The supernova explosions seeded the surrounding gas with heavy elements, providing the raw material for the next generation of stars. The process continued with successive generations of stars enriching the universe with progressively more heavy elements. Galaxies formed alongside this process of stellar evolution. The first galaxies were small and irregular, forming around the densest concentrations of matter in the early universe. Over time, these small galaxies merged with each other, producing larger galaxies. The mergers continued throughout cosmic history, and they are still continuing today. The Hercules Corona Borealis Great Wall in this picture must have begun forming very early in cosmic history. The structure we observe has been in place for about 10 billion years. The mass that constitutes it must have begun gravitationally collapsing toward its eventual configuration substantially before that, possibly within the first billion or 2 billion years after the Big Bang. The coherence of the structure, on scales of 10 or more billion light-years, implies that the initial seed pattern from which it formed was already coherent on similar scales. This is where the difficulty arises. The standard model of cosmology, with inflation providing the initial conditions, predicts that the seed pattern in the early universe was approximately scale invariant. There were fluctuations of all sizes, with smaller fluctuations being more common and larger fluctuations being progressively rarer. The largest fluctuations should not have been larger than approximately 1 billion light-years in their present-day extent. Fluctuations on that scale could grow gravitationally into the large structures we observe in the cosmic web. Fluctuations larger than that should not have existed. The Great Wall at 10 or 15 billion light-years requires either an initial fluctuation that was larger than the standard model predicts, or some kind of subsequent gravitational dynamics that produced a coherent structure from smaller initial fluctuations. Both possibilities are problematic. Producing larger initial fluctuations requires modifications to inflation that have not been independently supported. Producing coherent structures from smaller fluctuations on the relevant scales requires some kind of long-range force or coupling that is not part of standard physics. There are speculative proposals that might address these difficulties. Some involve modifications to gravity at very large scales. Others involve specific kinds of dark energy or dark matter with unusual properties. Still others involve the very early universe having more complex initial conditions. None has been definitively supported, but each represents a possible direction in which the cosmological framework might eventually be revised. What the wall tells us, in any case, is that the early universe was probably more interesting than the standard model has assumed. The seeds from which structure grew were either more varied, or more correlated, or otherwise different from what the standard picture suggests. The growth of structure was either faster or more complex than the standard simulations capture. Something happened in the early universe to produce a great wall, and whatever that something was, it is not currently part of our standard cosmological picture. The investigation of this question is ongoing. New observations, new simulations, and new theoretical work are all being pursued. The eventual resolution will probably involve some refinement of the standard model, or perhaps modest, perhaps substantial. The wall is one of the things forcing the refinement. By existing in the universe in a form that the existing theory does not predict, it is requiring the theory to do better. This is how cosmology has always made progress. Observations identify features of the universe that the existing theory does not explain. The theory is revised to accommodate the observations. The new theory makes new predictions. The new predictions are tested. The Great Wall is at one of the active points in this cycle, and the resolution will, in due course, be worked out. After more than a decade of study, the Hercules Corona Borealis Great Wall remains a structure surrounded by unanswered questions. The questions are not simply matters of detail. They are foundational questions about what the structure is, how it formed, and what its existence implies about the universe. Pulling them together in one place gives some sense of how much remains unresolved. The first question is whether the wall is truly a single coherent structure. The clustering of gamma-ray bursts is statistically significant, but the bursts are spread across an enormous range of distances and across a large region of the sky. Whether all the bursts actually trace the same physical structure, or whether the apparent clustering combines several separate structures that happen to lie near each other in our line of sight, is not entirely clear. The structure might be one wall 10 or 15 billion light-years across, or it might be several walls of more modest size, arranged in an alignment that gives the impression of a single larger structure. The second question is what the structure consists of in detail. We know it contains many galaxies, but the specific galaxy population, the proportions of different galaxy types, the chemical composition of the gas, the distribution of star-forming activity, and many other detailed properties have not been mapped. The structure has been identified primarily through gamma-ray bursts, which trace only a small fraction of the underlying galaxy population. A more complete picture would require direct surveys of galaxies in the relevant region at the relevant redshifts, which have not yet been conducted at the necessary level of detail. The third question is how the structure formed. The standard model of cosmology has difficulty producing structures of this size through ordinary gravitational growth. The required initial conditions or the required growth mechanism are not part of the standard picture. Various proposals for how the formation might have occurred have been advanced, but none has been confirmed. The formation of the Great Wall is, at present, a theoretical puzzle without a definitive solution. The fourth question is what the existence of the wall implies for the cosmological principle. If the principle is true at the largest scales, the wall is an extreme statistical fluctuation, improbable but not impossible. If the principle is false, the wall is a more typical feature of a universe that is more inhomogeneous than the principle assumes. Distinguishing between these possibilities requires either more data on similarly large structures or new theoretical insight into how such structures could be produced. Neither has yet been achieved at the level needed to settle the question. The fifth question is whether the wall is unique or one of many. Other very large structures have been identified, but none approaches the size of the Hercules Corona Borealis Great Wall. Whether this is because the wall is the unique extreme of a continuous distribution, or because there are other similarly large structures that have not yet been identified, is not known. Future surveys may identify additional large structures and clarify the situation, or they may confirm that the Hercules Corona Borealis Great Wall is, in some meaningful sense, the largest structure in the observable universe and remains alone in its category. The sixth question is what the wall reveals about the early universe. The structure was already in place at the redshifts we observe, which means it formed in the first few billion years of cosmic history. The conditions in the early universe that produced it are not directly accessible to observation. We can only infer them from the structure we now observe. What those conditions were and how they led to the wall's specific configuration is a question that will probably be addressed through some combination of theoretical work and detailed observations of the early universe through other means. The seventh question is what the wall tells us about the nature of physical law at the largest scales. Most of our physics has been verified at scales we can directly experiment with, laboratory scales, astronomical scales out to perhaps the size of galaxy clusters. At larger scales we extrapolate from what we know, but the extrapolation cannot be tested directly. The wall, if it really exists as described, may be probing the regime where the extrapolation fails. If so, it could reveal aspects of physical law that we have not previously been able to study. The eighth question is whether we will eventually understand the wall fully. Some questions in science get resolved. Others remain open for long periods, sometimes indefinitely. The history of cosmology suggests that major questions usually do eventually find answers, but the timescales involved can be substantial. What is clear is that the wall has become a focal point for thinking about all of these questions. It is not just a structure to be studied in isolation. It's a probe of cosmological theory, of structure formation, of the early universe, and of the limits of our methods. Each unanswered question about the wall is connected to broader questions about the universe. The investigation continues, and the answers, when they come, will reach far beyond the specific structure that has provoked the investigation. What is left to say about a structure that we cannot fully see, cannot fully explain, and cannot definitively prove? The earlier sections covered what the wall is, how it was found, and why it is difficult to understand. This final section is about what it is like to live in a universe that contains something like this. Something so large that the words for size are no longer adequate. Something so distant that the light from it predates the planet on which you are listening to this recording. something so unexplained that the people who study it for a living have not resolved the basic questions about it. The difficulty is not a failure. It is a feature of the work. Science often proceeds by identifying something interesting, working on it for a long time, accumulating partial answers, and eventually understanding it well enough to move on. The Great Wall is currently in the middle phase of this process. We have identified it. We are working on it. We have partial answers and lingering questions. Whether we will eventually understand it fully and how long that will take is not something we can predict from where we are now. The Wall is one of many things in the universe that we do not yet fully understand. Dark matter is another, dark energy is another, the values of the constants of physics, the very early moments of the universe. The list could go on. The Wall is in good company. Living with this kind of incomplete understanding is the normal condition of being a thinking species in a complicated universe. There is a certain quality of feeling that comes from contemplating something this large. It is not the feeling of being made small. It is not the feeling of insignificance. It is something more like the feeling of standing at the edge of a forest at twilight and realizing that the forest continues in directions you cannot see for a long way beyond what is visible. The forest is there. You are at its edge. The continuation is what it is, regardless of whether you walk into it or remain at its edge. The Great Wall is, in this sense, the edge of what we currently know. There is more universe beyond it, presumably containing more structures we have not yet detected. There is also more theoretical understanding to be developed, more data to be collected, more questions to be asked. The edge moves as we work. The Wall marks one location of the edge at the moment of this recording. The edge will be somewhere else in the future. What is certain is that the work continues, and that the relationship between us and the universe we are investigating has its own slow pace. It is worth lingering on the slowness. The Wall has existed for billions of years before any species existed to wonder about it. It will continue to exist for billions of years after the species that wondered about it is gone. The light arriving from it tonight left when there were no eyes anywhere to receive light at all. The instruments that detect that light were built by a civilization that emerged late in cosmic history, and that will, in the long run, give way to whatever comes next. The Wall does not notice any of this. It is not a participant in the timeline of our knowing. It is simply present. The act of knowing about it is something that happens here, on this small planet, during this small window of cosmic time. None of this requires action on your part. The Wall is not asking anything of you. It is not threatening you. It is not communicating with you. It simply exists at a great distance with properties we are slowly learning to characterize. The act of learning about it is the only relationship we have to it. There is finally the simple fact that the universe is much larger than we are. The Wall is one of the more striking ways in which this fact is brought home. There are structures so large that they exceed the predictions of our theories. Light so old that it predates our planet. Distances so great that the words used to describe them no longer connect to anything in human experience. All of this is true. All of this is part of the universe in which you are listening to this recording. The recording will end, the structures will remain, the light will continue to arrive. You can rest in this. The work is being done, the questions are being asked, the Wall is being studied. None of this depends on you in any specific way. The investigation is being conducted by people who have devoted their careers to it, and the conclusions, when they come, will be shared with everyone who cares to learn them. For now, the structure is there. The light from it is arriving. The questions about it remain. The universe continues. So, due time will the answers.